My name's Hugo and Anderson, and I'm co-teaching this workshop with old mate Eric Marr over there. Eric and I have been collaborators and, more importantly, friends for a couple of years, and developed a lot of educational material together. We're very excited though. This is the first time we're co-teaching in person together, which is really exciting. Before we get started, I just wanted to give a few words about kind of the structure of today's workshop. We'll be working in Jupyter Notebooks. Spend the first hour or so just thinking about probability in general and using NumPy's random number generator to figure out a few things about probability, joint probabilities, conditional probabilities. These are all concepts that you will have heard of and seen before from a relatively early age, but we're going to play around with what's now referred to as hacker statistics, so using computation to think about statistics and probability, which is a lot of fun in my opinion. Then we're going to start really thinking about Bayes' theorem and Bayesian inference and the basic ideas of priors, likelihood functions, and posteriors. And we're going to do that using random number generators, but then we're going to jump in and start using PyMC3, which is, as we'll see, a probabilistic programming language that allows us to express kind of how we think about Bayesian inference very beautifully in code with an API that really reflects how we think about it. That will occupy the first 2 hours. Then Eric's going to jump in and show you all of the really strong power of PyMC3 in terms of thinking about hypothesis testing, parameter estimation, and in the end, hierarchical modeling, which is a really fun thing to do. I'd just like to get a show of hands. Who's used NumPy's random number generator before? Cool. Okay. Who's used PyMC3? Who's used any other form of probabilistic programming? Okay, cool. Well, that's good to know. So I think to get started, let's just run the first code cell, which is in the student notebook. So this is the first student notebook, 01 student. Okay, and this is what is probability, a simulated introduction. Okay. So we're going to run that, and then we're going to have a little chat about all of this and what probability really represents and how we think about it in a variety of ways. So several hundred years ago, Reverend Bayes, among other people, actually thought about probability in terms of how certain we are about particular things, the degree of belief we have about, let's say, the rate of prevalence of a disease, or the bias associated with flipping a coin are two examples which kind of equate to the same things, as we'll see in a lot of ways. This was quite difficult for a lot of working scientists to grasp at that time, and we didn't have computational engines that could really power through the work that needed to be done. And so this idea of frequentism emerged, where probability would no longer represent a degree of belief, but it would really represent the long-run frequency of the experiment, of simulating the probability distribution. So the idea of frequentism is you do the experiment 10,000, 100,000, a million times, and this is really the probability, what probability means, which philosophically is very different. So frequentism says that this is really the only way we can talk about probability, and it made sense in terms of kind of experimental and lack of computational power at the time. Whereas Bayesians really think about it in terms of degree of belief, and we'll see that the posterior distribution, and if you don't know that term yet, don't worry about it, we'll get there. You'll probably be sick of it by the end of these 4 hours. We'll see that this really represents finally what our degree of belief around our model and system parameters are, okay? So the example I give in this notebook, in terms of random probabilistic phenomena we're talking about, is if you know that a website, for example, has a click-through rate of 10%, and that means that 10% of people who visit it will click through on a particular hyperlink to end up somewhere else, we can then calculate the probability of having, when choosing 10 random people, of having 9 people, 8 people, 7 people click through, okay? But having said that, if we collect a bunch of data, then how do we actually figure out what the actual click-through rate is? You can ask the same about prevalence of disease, of the probability of flipping a head when flipping a coin, or in fact, you know, most models, you can ask similar questions. And the point is that science actually mostly asks questions of this second kind, right? We have some idea of how our system works, but then we collect data and we want to know more about the system and our model and what type of values for these parameters, well, our degree of belief around what these parameters can be. And Bayesian thinking provides a very robust way of thinking about this. And in fact, I've written this in the notebook, but I'm going to speak into both microphones at the same time. I'm going to just write this up. Essentially, what I've told you is that we really know how to think about the probability of getting some sort of data given a model, right? Knowing that the click-through rate is 10%, right? Or whatever it is. And the way we express that, and we'll see more of this, is the probability of data given, vertical line, given the model. We know how to calculate these types of things. And in fact, we're about to do it using NumPy's random number generator, right? What we're not good at is thinking about the probability of a particular model given data, okay? And that's precisely what we're going to see that Bayesian inference can be very powerful at doing today. So without further ado, this is going to get weird using both mics. Without further ado, we're going to jump in and start using NumPy's random number generator to simulate some stuff, okay? So firstly, let's say that a website has a click-through rate of 50%. That means 50% of people click through. So what we're going to do is we're going to simulate this. We're going to simulate picking 1,000 people at random from the population and see how likely it is that a certain number of people click, okay? So before we do this though, we're just going to use the basic np.random.rand to randomly select floats between 0 and 1, which is what this function does. Okay, so just in these sections, you're just going to code along with me, and I'm going to use tab complete occasionally. Okay, so we're going to choose 1,000 samples, and then we're going to use matplotlib to plot it. I'm going to execute that cell. Okay, and note, this is actually a histogram, and if you wanted to make it kind of a frequency distribution function, you'd change what's happening on the x-axis to have proportions instead. But this is just a basic idea of how to sample using NumPy and then to plot what's happening there. Okay, but this isn't really what we want to do, right? What we want to do is sample from this population of people clicking through or not. Okay, so remember that in this toy example we're doing, there's a click-through rate of 50%. So what we can do is we can look at each number that was generated by this uniform distribution and just see whether it was below 0.5 or not, okay? And if it was below 0.5, we'll say that person clicked through. Okay, so clicks, the next cell is X. Is it less than 0.5? And just remember that this will give us an array of booleans, of trues and falses, which you can perform arithmetic operations with. So if we have an array of trues and falses, we can then take the sum of them to get the total number of clicks, right? That's the total number of trues, essentially. And then I'm just going to print out a string that number of clicks is equal to whatever this variable has evaluated, this name n_clicks has evaluated to. And this uses something called fstrings, which was one of the great things about Python 3.6, one of the many great things about 3.6, if I remember correctly. I'd hate for someone to be like, no, the greatest thing about 3.6 was something that you don't even know about. Okay, so I've clearly done something wrong. What I've done is I've taken the sum, that's the total number of clicks in this, but what I want to do is divide by the total number of people, which is the length of X, okay? And now what we see is that the number of, I'm sorry, no, I was absolutely right. I'm putting the, what do they say, putting the cart in front of the horse. Is that a saying? Wait. Yeah, okay, that's what I did. Okay, so the number. Yeah, great. Look at you all. You all should be teaching this. No, I'm kidding. So yeah, so the total number of clicks was 484, which is around 0.5, right? The reason we didn't get 500 is because this is a random process, right? And we're using a random number generator, so it will never be absolutely on point. So now what I wanted to do, and this is the cart, that was the horse, and this is the cart. So the proportion that clicked is number of clicks over the length of click. Okay, so the proportion who clicked was 0.484. Okay, that's cool. So I suppose I've already answered this. Did you get the same answer as your neighbor? This is for discussion, and I'm going to discuss it. The answer is no. I'd be very surprised unless you both set the same seed, which if you don't know what that means, you'll know very soon. Which also would be weird if somehow two random people set the same seed. And the reason you didn't get the same answer is because this is a random process, okay? So now I just want to go back and think very briefly about the idea of the probability of a model or the probability of the parameter click-through rate given the data. So now we've simulated this. We have our data and we have the proportion who clicked through was 0.484. Let's say all you had was this data and you wanted to figure out the click-through rate, okay? Now, I'd like someone to let me know what your estimate for the click-through rate would be. Come on, there must be an extrovert in this room. Yeah, so it's going to be, you'd think 48.4. Why would you think that? Is it the so the thing is we actually have 1,000 samples, right? We have 1,000 data points. So why does this calculation, this is something we do as children intuitively, actually. When thinking about numbers, you know, we're taught in a particular way that will lead us to feel this type of thing. The reason this is the case is because this is actually the maximum likelihood estimate for the click-through rate, okay? And we'll see a bit more about that later and how Bayesian inference can give us a way of thinking about this. For bonus points, how confident would you be of this estimate? Because I don't have a clue yet, right? So I would say my sample size was 1,000, so kind of pretty confident in some way. What we'll see Bayesian thinking actually gives us is an entire distribution of possible values, and we'll actually see that around here is where the peak is, okay? And it will give us uncertainty around it, and we can answer any questions about the distribution of possible answers to this question, which represent our degree of belief, which I find very exciting. Okay, now I'm just going to give a small note because I don't want to go down this rabbit hole. We've described probability in two ways, in terms of a degree of belief and in terms of long-term frequencies, right? Now, these are both kind of relatively vague ways of speaking about probability. What I want to say is that probability actually, it defines a function from the space of possible values. This is also vague. In this case, it's the interval 0, 1 that describes how likely it is to get a particular point or region in that space. For those a bit more mathematically inclined, I'd very much recommend Mike Bedencourt's very elegant Intro to Probability Theory. Mike's one of the core devs and co-maintainer of the probabilistic programming language Stan, and also if there's anything you don't understand there, or he's very approachable, and you could even issue a pull request to this material, which I'm sure he'd appreciate more than an issue. Having said all of that, let's just get you all working. Very briefly, take 5 minutes to answer this question and write the code to do so. So it's pretty similar to the code that we've just written. So I want you to use random sampling to simulate how many people out of 1,000 click when the CTR is 0.7. So how many click and what's the proportion? So just let's try to get this done in 3 to 4 minutes, maybe 5. When you've completed it, put up your blue sticky on your laptop. And if you have any questions, put up the red one. Also, there are solution notebooks. Do not look at them, okay? Because I've introduced strategic errors into those currently. And after the workshop, I'll push the correct solutions. No, I'm kidding. They're not strategic errors. They were accidental, actually. Okay, I see a sea of blue emerging. This is wonderful. What I'm going to do is I'm going to quickly code it myself, and for those of you who are getting there, you can code along for what you haven't written yet. Okay, so we've actually already generated 1,000 random samples, but what I'm going to do is do that again, because we don't necessarily want to keep using the same random samples every time. So np.random. .rand 1,000. Now to get this Boolean array, what do I actually want? I want it less than 0.7, right? I actually think the notebook has 0.3 or something like that. So that was my non-strategic error. The number of clicks will be sum of clicks. And to print this, we do number of clicks. Whoa. Great. And then once again, we want, for the proportion, we want the number of clicks, but we want to divide by the total number of people. So that's the length of clicks. And we see we got 725, which is just above 0.7. Great. The proportion who clicked was 72.5% of people. So that's our estimate of the click-through rate, which we can actually see isn't, I mean, it isn't 70, right? It's 2.5% more, so maybe that's not close enough for us. But having said that, there's a discussion point which once again I'll discuss. I mentioned before that a very common model that a lot of you may have heard before is this idea of a biased coin flip. Now, one of the reasons, a couple of people I spoke to and got feedback on this workshop from said just use the coin at the start. And I was like, people hate the coin. The coin flip is, you know, because there aren't any biased coins, essentially, right? So it doesn't model, except maybe in a casino, the crazy coin. It doesn't model any real world phenomena in terms of actual coins. But this model is known as a biased coin flip because we have it's a probability of a binary outcome, right? So you've got click through or not, okay? And we're modeling that with a particular probability, right? Which you can think of in terms of, it's exactly the same model that you'd have with a coin flipping heads or not with a particular probability. The same as you think about prevalence of disease in a population. So someone has a disease or not. So it's actually an incredibly useful model when thinking about real world phenomena. Okay. So without further ado, I want to introduce you to one of my favorite data sets, which is the Galapagos finch beaks dataset, which I've linked to here. And over decades, several people have gone and measured these beaks of different species on, I think it's the island of Daphne Major. I'd say that with certainty, except this is being recorded, so I want to leave myself an out. Okay, but what we're going to do is we're going to load in this dataset and check out the head. Okay, so this is just a bit of pandas. Okay, so we see we have a column species, then beak length and beak depth, okay? Now, what I'm first going to do is just take out the lengths. Just wondering, what's the data frame called? DF12. I apologize for such a horrible name for a data frame. I usually say name things appropriately and well, so you know what they are, and I haven't done that here. The reason I did that is I think these measurements are from 2012, this particular one. So we're gonna take out the lengths, okay? Now, we're thinking about proportion and probability and all of these things. So I wanna know what proportion of birds have a beak length of 10, okay? So the way I think about that is I'll take the sum of the Boolean of lengths greater than 10, and just print that out, okay? So actually, no, that's not the proportion again. So then I want the length of lengths, okay? So 85%, around 85.1%, okay? So, and I just want to stress that this is a proportion, not a probability. You may want to think of it as an estimate of a population probability. So the probability of if you draw a bird, of it having a particular beak length. But I want to stress that these are different things. Oh, and that's what I've written below. Okay, great. Having said that, we've calculated a proportion, not a probability. But what we're going to do in terms of thinking about sampling techniques to think about probability, we're going to use this proportion as a proxy for probability. But we're going to do it in a slightly different way, which we'll generalize soon, okay? So we're going to use this idea of resampling. In a sense, it's very similar to bootstrapping what we're doing. We're going to simulate drawing random samples from this empirical data, but we're going to allow to draw repeat measurements, okay, in order to see how many lengths or the probability of getting a length are greater than 10. Okay, so we're going to have that many samples, and then once again we're going to take the sum. Now, to draw random samples, we're going to use a function called, I think we're going to use, there are many ways to there are several ways to do this. We're going to use random choice, random.choice. So we're going to choose from the lengths, okay? Now, how many are we going to choose? We're going to choose n samples, which is 10,000 in this case, and we're going to allow to draw with replacement. Okay, so we're going to put the keyword argument replace equal true. Now, we want to know how many of these are going to be greater than 10. So once again, we do this. So in here, we get our Boolean array, and then we're going to divide by the total number of samples. Okay? And we saw it's relatively close to what we had earlier. Okay, so that's 85.6%. Cool. So we've simulated coin flips by drawing from a uniform distribution where the probability of getting anything between 0 and 1 is the same. Now, and then looking at the proportion of how many of these draws was less than our probability, right? Now, what we're essentially doing is we're building another distribution in doing that. Does anybody know what the name of the distribution that describes how many successes or failures or heads or tails is called out of a number of coin flips? Binomial. Exactly. It's called the binomial distribution. And so what we can actually do, NumPy has this built in. We've done it by hand, but you can use the binomial distribution, which, you know, when developing more complex simulation models, or simulations of models rather, you'll see it'll actually become a lot easier. Okay, so that's exactly what I've written here. You've used the uniform distribution to sample from a series of biased coin flips. Now, we'll use the binomial distribution, which is defined as the probability distribution of the number of heads seen when flipping a coin n times, when the probability of heads is this p. And we have two parameters, n, which is the number of flips, and p, the bias, so the probability of seeing heads. As I've said here, the distribution tells the story of a general model, and that's precisely what we discussed with respect to the examples of click-through rate and any other number of phenomena. Okay, so now we're going to use the binomial distribution to answer the same question as above. If p of heads is 0.7 and you flip the coin 10 times, how many heads will come up? Okay, so what I'm first going to do is set the seed. And is it? It's, of course. And I am going to set it to my birth date. I know you'd want to see a 0 first there if you're from the United States, but in Australia we do it the right way. No, I'm kidding. I do everything inconsistently now. This is the worst thing about my life, essentially, which isn't that bad. But when I write stuff now, like I'll use color with an OU, then center with an RE, and say entree for a main course, and that's the worst, by the way. Entree literally means entry in French. That's why it's called. Okay. Okay. So what we're going to do is we're going to simulate from the binomial distribution. Okay. So np.random.binomial, and how many flips we're going to have 10 flips, and we're going to have a probability, or our P is 0.7. So let's execute this. And right, so that's interesting. Got 7 heads, which you may think, oh, okay, it's 0.7, so that makes sense. Do not think that, because we could also have got 8 relatively easily, or 9 or 6, okay? Perhaps if you used a different seed, that wasn't my birthday. Feel weird that now you all know that my birthday is in a couple of weeks, so feel free to reach out with wishes of joy and prosperity. So the great thing is now that we can just add an extra argument to this random dot binomial in order to simulate 10,000 flips. We've got a question, yeah?
Yeah, wouldn't you want the first argument to be actually 1, so that you pick 0 or 1 heads or tails? And are you not picking, every draw of it is 1 heads or a tail, right? So getting 7 is it's picking from possible classes, 10 different classes. It's picking with some probability 0.7.
No, so the first argument is the sample size, and the second argument is the probability. So it's literally, we've got this, the binomial distribution with parameters n and p is defined as the number of the probability distribution of the number of heads you'll see when flipping it. So to figure out how many times we want to run this simulation, we then have the third argument. Does that make sense? Okay. Exactly. So, but that is an important question. So, so as I write here, we've simulated the scenario once, okay? But in order to get this kind of frequency of distribution, the actual probability distribution, we want to do it many times. So we're going to do np.random.binomial, and we're going to do 10, 0.7, and we're going to do it 10,000 times. Okay, and I've included the normalized histogram in here, which essentially is our proxy for a probability distribution, okay? Great. Okay, so this is really cool, right? This is exactly the problem that I discussed above, that given the model, we can get out the distribution of possible results, the data, okay? So we see, okay, that 7 occurs just over like 26% of the time. 8 occurs quite a bit, 8 and 9, then 10. The bins may be slightly off, but you get an idea of the shape. We can see in this simulation, we haven't got 0 at all. If you simulated enough, you would see 0 heads, but with very low probability. So maybe you'd want to simulate 100,000 or 1,000,000 times to make sure that you see everything. The idea of how many times to simulate something is a great question, which I won't answer right now, but we'll see a bit later when thinking about sampling from posterior distributions, kind of rules of thumb about this. So that was the group chat. What do you see in the above? So now I'd like y'all to, as soon as I get to Texas, I start saying y'all, to do this hands-on. So if I or you flip a biased coin with probability of heads equal to 3, 20 times, what is the probability of 5 or more heads? And there are a couple more questions there that I'd like you to answer. I'd like you to take 5, maybe a few more minutes to do this. Okay.
Put your stickies down.
Yeah, of course. Sorry, blue stickies down, because otherwise I'd be like, hey, everyone's done already. And okay, so I'm going to take you through my way of answering this. We just had a great question from my friend in the middle there. Are we still calculating probabilities, or are these actually proportions? Now, we're estimating the probability using random sampling, okay? The reason it's not quite a proportion is the proportion is from a finite empirical data, essentially. That's when you get the proportion. If you've actually got a random number generator generating all possibilities, we're actually estimating the probability. And that's a subtlety that I would say you're estimating the probability rather than calculating it per se. But that's a very good question. And we'll see when we start sampling for posterior distributions later on that we're doing something very much akin to that. But that is a fantastic question. So what I'm going to do is just take you through this. So we're flipping it 20 times. So we're going to, once again, look at the sum. We're going to sum up all the times that we get a head, okay? So, or all the times we see 5 or more heads. So we're going to generate a bunch of binomials. We're going to flip a coin 20 times, right? And then we're going to have probability 0.3, and we're going to do this. Now, I didn't specify this, but I'm going to do it 10,000 times. And we want to know how many times we actually see 5 or more heads there. So how many times is that greater than or equal to 5? I'm going to divide this by the total number, which is 10,000, okay? And execute that. I've got 76.13. Now, if you set the seed as my birthday, which I don't know whether people do that or if that'd even be creepy or whatever when I didn't give any instruction, but you would get the same thing. Unless you've run different cells in the meantime. If I flip a fair coin this many times, what's the probability? Now, this is one of the cool things. You know, we can repurpose our code. It's actually exactly the same code with a different probability there, okay? So, here's that 0.5. And look, if it's a fair coin, that makes sense, right? That we'd think we'd have a lot of times of getting 5 or more heads with 20 flips if it's a fair coin, right? Now, the last thing is plot the normalized histogram. And how am I going to do that? It's flipping a fair coin 10 times. So I'm going to get this. So I'm flipping it 10 times, and it's a fair coin, so 0.5 probability. And now what I want to do is plot the hist of x, and I want it to be a density, which means we have frequencies, not counts, as we'll see. And what I mean by that is we have frequencies on the y-axis, and this, so we'll see, you know, the lion's share happen in the middle, and we have tails on either side. We have a minimum of 0 and maximum of 10. Does this distribution look like anything to anyone? Looks kind of Gaussian. We can chat about why that might be the case at some point. Now, before we go on, something very important I need to tell you, okay? I'll get the MC mic for that. It'd be difficult to do a mic drop with this one. So the point is that I've done something really bad in teaching you this. I've convolved the concepts and coupled the concepts of probability mass functions and probability distribution functions. And I just wanted to give a small word to this. A lot of good references, such as Sivir and Skilling, which we'll put in the additional resources, deal with this a great deal. The point is that the binomial distribution has a discrete number of possibilities, right? You can get 0, 1, 2, 3, up to however many heads, okay? Whereas the uniform distribution is any values between 0 and 1. So it's continuous in that sense. And the reason this is really important to recognize is that this marker is horrible. Is that the uniform distribution, and this is a stumbling point for so many people, it goes from 0 to 1, and it's defined as 1. That shouldn't be there. Well, it's defined as 1 for every value between 0 and 1, okay? Now, that does not mean that the probability of getting 0.3 is 1. That would be absolutely crazy. That would mean the probability of getting every value is 1, okay? Now, that is not the case. This type of thing, called a probability distribution function, not like the binomial, which is a probability mass function, what this means is that we think about not the probability of getting an individual value, because in fact, the probability of getting any specific value is 0, right? We think about getting the probability of values on essentially open sets or intervals, right? So the probability of getting between 0.3 and 0.5 is the area of this rectangle. So the probability of getting this is going to be 0.2. Anybody who saw this without these words would be absolutely mystified by what that means. But it's the area here, okay? Now, this is one of the biggest stumbling blocks for me, because time and time again I've tried to teach these types of methods without using calculus. But in the end, you're actually, I think, essentially, via computational methods, you don't need the calculus. We've avoided that. But you need to be able to talk about it. And in the end, you need to be able to talk about either integrals or very large sums. So essentially, that's what's happening here. And that's really all I want to say about this. And I love chatting about this, particularly over beers and queso in Austin. So we can do that. I couldn't figure out which mic to keep using. Okay, great. So now we're going to move on to talk about joint probability and conditional probability. Now there are some hands-on exercises in this which I really want us to get to the one at the end. So we may move a bit more quickly through this section in order to get to this one at the end and then move on to looking at priors, posteriors and likelihoods. A joint probability essentially is the probability of two events both occurring. So for example, we've seen getting several heads in a row as being a probability, but you can think of that as a joint probability of getting two heads in a row, okay? Now, one thing worth mentioning is if two events A and B are independent, like in the coin flip example, then the probability of seeing A and B is the probability of A times the probability of B. Now note that you've got no reason to think two things are going to be independent. You need to prove to me well before saying it that this is the case. And I think most of us would know this from school that we consider this as the and being multiplication, right? So the probability of A and B is the probability of A multiplied by the probability of B. Okay. And if that's stating the obvious, that's really good. So what we're going to do is we're going to verify that this is the case in the two coin flip case. Just give me 1 second. Okay. So the way we're going to do that is we're going to generate the data of two coins being flipped together first, and then we're going to generate the data and check out what the estimate of the probability is. Then we're going to generate them being flipped together and see the same thing. Okay. So np.random.binomial. We've got two fair coins. Flip them 1,000 times. Now the probability of getting two heads is going to be the sum of x0. We want to see it's actually equal to 2. And remember, for getting a Boolean a true or false out with respect to a quality, we use the double equal sign over the length of, what have I done here? Okay. Yep. Over the length of x0. I'm going to plot the histogram of results. And what do we really know that the probability of seeing two heads is? 25%. It wasn't a trick question. Okay, yeah, and we got 24.4, and we've got out our, I might hit density equal to true as well to actually get that out, okay? Beautiful. Yep. Now, what we're going to do is calculate PA times PB, okay? So the probability of seeing one head, then the probability of seeing another. And I'm going to cheat slightly by just copying and pasting this. The probability, whoa, what happened there? Okay, I was in the wrong cell. Probability here is x1, we want to be equal to 1. We want to see one head, and then we want the same for x2. And once again, we see around 25%, okay? So this is one way to kind of think about, without actually doing the calculations of probability, to think about using sampling and resampling techniques to think about joint probability. Now there's a hands-on here for you to do the same. I'm going to leave that as a homework exercise because we've got time for either the hands-on with this or the hands-on with conditional probability. And the conditional probability one is really, really fun and illuminating. Not that this one isn't, but it's even more so. Okay. Once again, I'm going to say this all the time, that we are using proportion in our simulations as a proxy for probability, which once again is so useful to start thinking about probability with respect to simulation. Okay, so now let's think about conditional probability, okay? So it's the probability of one thing conditioned on another. So one example is we can think of the probability, we've seen the probability of a finch having a beak of a certain length. We can think about the probability of a finch beak having, I've got depth there for some reason. I actually want that to be length, so I'm gonna change that. Please do that as well in your notebook. But we can then have a look at the probability of a finch beak having a certain length given on if it's of species Fortis or Scandens, for example. And that's what we're going to do now. So once again, we're going to look at DF12 and look at the column beak length. Is that what it's called? Yep. Length. And see how many of those are greater than 10 and divide that by, so I think that's what I want to do. Yeah, so as we saw before, 85% have a length greater than 10, okay? Now we're going to do the same, but we're going to do it for Fortis, and what I've done here is I've just used some pandas to subset the data frame. So we're going to now, do it with Fortis. Okay, so now suddenly we see that 69% have a certain beak length. So conditioning on that has actually let us know something about our population. Eric, would you mind just closing the door if it's open? And now let's do the same for Scandens. What would you expect Scandens to be higher or lower than Fortis? Yeah, great. That's really good. The alternative is scary. Okay, so let's have a look at that. Wow, okay, so now we see with Scandens that every bird had a beak length of greater than 10, okay? Which, and for me, that shows that conditioning is actually pretty important already, right? So just a quick note that these proportions are definitely different. Can't say much more currently, but we'll see in later on in this workshop how to robustly think about whether these populations are actually different. And so I've given an equation based on how to relate joint and conditional probabilities, which I'll write up on the board as well. No, I won't. I'll leave it there because it's on the screen. The probability of A and B is the probability of B multiplied by the probability of A given B, okay? And a homework exercise for those interested, you can verify the above relationship using these types of simulation and resampling techniques, okay? So now this is the really fun part. I think it's really fun. It's a drug testing example, which I repurposed from Wikipedia, in fact. I don't know if I've referenced that. Definitely need to. The question is that suppose that a test for a particular drug is 99% sensitive and 99% specific. So that means that we'll get true positives 99% of the time for drug users and true negatives 99% of the time for non-drug users. Suppose that 5 in 1,000 of people are users of the drug. What is the probability that if you select an individual with a positive test, that they're actually a drug user? So what we're actually thinking about here is we're thinking about calculating P of the probability of them being a user given they have a positive test, okay? But what do we know? We know that it's 99% sensitive, which means we know what the probability of them having a positive test being a user is. So this is a known, and what you're going to do is use simulation techniques to figure out this quantity here, okay? And it's not obvious for me how to move between them before we either simulate it or discover Bayes' theorem, which we will after the fact. And if you notice an analogy between these two systems, well done. So take 5, maybe a bit more minutes to do this. I've given the names there and ask the questions in line in the code to give as much skeleton as possible. And if you have any questions, so yeah, take off the blue stickies. And if you have any questions, put up the red sticky and enjoy. And maybe actually, before you do anything, think about what the answer to the question could be. Maybe take a minute to think through that. Okay, well, I'm gonna start just going through a bit of this. So I want to sample for the number of users, okay? And I know how many % of people in the population are users. So what type of distribution would I want to sample from there? Binomial, exactly. I rarely ask trick questions. Okay, so we know how many n. What's the p in this case? What proportion of people are users? And I messed this up at one point when I was actually writing this. 0.005 exactly. Okay, 5 in 1,000. Okay, and that's it. So, how many non-users are there? It's n minus the number of users. Okay. So I execute that, we're good, okay? So how many of these users tested positive, okay? Once again, I've got this population of users, and I know that 99% of them will test positive. So once again, I'll want to use a binomial distribution, right? So I sample from the binomial. So np.random.binomial. And our sample size is the number of users, right? And 99% will test positive, okay? Now, the non-users, right? We know how many of those will have a negative test. We know what the specificity is there, right? But that isn't quite the question that I've asked. I've asked how many will have a positive test. So we know 99% will come up negative. So once again, I have the number of non-users. How many will come up positive? 0.01, exactly. Okay, so now the question is, we know how many people have tested positive. Now, how many of those were actually users, okay? So to figure out that ratio, we divide the number of users by the actually positive users and the non-positive users, okay? And we see that, this is crazy. We see that the probability that someone randomly selected who gets a positive test is actually a drug user is 33%, although the test is 99% specific and 99% sensitive. So does that seem counterintuitive in some way, at least at first sight? I think it does. Can anybody tell me why this is the case? So it's correct first, okay? Step 1, step 0, we'll zero index with steps. Can anyone tell me why this is correct?
The incidence of drug users is really, really low. So having such a high specificity, the high specificity or sensitivity is not really that high.
Yeah.
Because incidence is already very low.
Exactly. So our friend here just said that the actual proportion of people who use the drug is so low that the people who don't use it is so high, and that the false negatives in that case drown out a lot of the true positives, okay? So that 1% of people who are negative that test positive, right? Okay, I'm getting lost in my words here. The proportion of people who test negative but are positive is so, okay, let me try that one more time. Okay, the people who are non-users is so high that the 1% of those who test positive but they're non-users is actually a large proportion of the population, okay? That's what's happening there. So what we've seen, and this is I call this a key note. I realize at a conference that's probably a weird thing to call a note. Fundamental note. I should call keynotes fundamental notes now, I think. So this exactly is related to this switcheroo we did between P of data given model and P of model given data, with P of user given positive to P of positive given user, okay? Now, what we've essentially done is just demonstrated Bayes' theorem using simulation techniques, okay? So if there's one takeaway I want you to get is that knowing how to simulate probabilities, knowing how to simulate joint probabilities, and knowing how to simulate conditional probabilities allows us to prove fundamental theorems in probability theory. Well, not to prove them, but to demonstrate them, actually. Of course, the actual proof of Bayes' theorem is so elegant that we can just do it on the board, which I'm about to do, which allows us to move between these two different forms. And if you take anything away from this hour, I'd really like it to be how we can relate these, this to that and that to that. So what I'm going to do, I might erase this and to the best of my ability. The light one can't even be erased properly. And so what I'll do is show you that we're really interested in moving between the probability of B given A and the probability of A given B, where one is data, one is model, one is positive, one is test, and so forth, okay? And the way we do this is, I want you to recall that the probability of A and B is equal to the probability of A given B times the probability of B. So we want B and we want A, knowing that B is the case, okay? That's one of our fundamental rules of probability. Now, this is also equal to the probability, due to symmetry, of B and A, right? So if we look at this equation here, we can replicate it and switch them around. Probability of B given A times the probability of A. Okay, so what we see, I mean, my background's actually in pure math and applied math originally. This is a horrible way to write equality. But all of these four things are equal. I hope my grad school advisor never sees this video. Okay, but if we know that these two are equal, what we actually do is we want to know the probability of B given A. If we know the probability of A given B, we can divide both of these by the probability of A, right? So this just becomes the probability of B given A, and here we get the probability of A given B times the probability of A over the probability of, I'm sorry, that's going to be A. At the last moment, he stuffs up. Okay, and this is Bayes' theorem. That's what Bayes' theorem is, okay? And this is going to be the fundamental theorem that will allow us to think about how to calculate probabilities of models and parameters giving empirical data that we've collected in the world, okay? And that's really cool to me, and I think it probably is to you, and that's why we're all here. So to really kind of drive it home, what I want to say is that we're really interested in the probability of models given empirical data. And what we can say now is that the probability of a model in the whole world of possible models given data is the probability of data given the model. Now we know how to calculate that. That's actually what we've just been doing for an hour, essentially. The probability of data giving a model, we can do it simulating it. There are a number of other ways to do it. We can calculate it analytically using math, a different form of math, times the probability of a model over the probability of actually seeing the data in the first place. Now, this is a slightly strange term that I want to say a bit about, okay? Now, generally, if we want the probability of a model, right, in the whole world of models, all we really care about is how it relates to the probability of other models, or the probability of parameters, how it relates to the probability of other parameters, okay? So in fact, because this term isn't dependent on the model at all we think is about proportionality, right? Or relative probability. So the probability of a model giving data is proportional to the probability of data given model times the probability of the model before we saw any data, okay? Now, these three things have terms. Okay. Probability of a model before seeing any data essentially is the probability of something prior to seeing the data. That's why this is called the prior. All of this is in the notes as well, in the notebooks. Okay. The probability of seeing some data given a model, we can also call that the likelihood of seeing data given a model. Okay? So this, I've really put myself in a funny little box here, is the likelihood. And this, because it's the probability of the model after the data, post means after, it's kind of Latinate. We call this the posterior. I'm laughing because I just remembered, and this isn't safe for work or conferences necessarily. I remember the joke Alan Downey's joke about the posterior that we can tell that joke over beer and queso as well. So essentially, this is the fundamental idea of Bayesian inference and Bayesian thinking. So one challenge people have is, how do I know my prior? We're going to discuss different types of priors, okay? If you don't have a lot of data, right, your posterior may look kind of like your prior because there's not much happening here. As you collect more and more data in the phenomenal empirical world, this term, the likelihood, starts to dominate. And as we'll see, the more and more data you collect, the less relevant your prior will be, okay? So that's what we're going to get into now. And this stuff, this is why I want you to use SciPy widgets, because what we're going to do is we're going to build a plot of our posterior and see how it varies as we increase the amount of data that we have, which is one of the, and it's quite illuminating, I think. So what I'll get you to do now is to open the second notebook. And what we'll do, we'll execute all our imports at the start. Now, everything I've just said is really in this section entitled From Bayes' Theorem to Bayesian Inference. Okay? So, once again, I said our statistical intuition will tell us that our best estimate of the probability of heads is the number of heads divided by the total number of flips. Now what we'll see is when we calculate this posterior, we'll have the entire distribution, which is really damn cool, I think. And the other thing that this does is, as I've written, it doesn't tell us how certain we can be of that estimate, and it also doesn't extend to more complex examples, okay? Now, all of this I've just gone through. I want to make a quick note, and this is really important, that something I've done here and something we've done culturally is totally overloaded the term probability, okay? So I've used the word probability to mean this P, which is the probability of seeing heads when flipping a coin. I've also used the word probability when talking about the binomial probability distribution, so the probability of seeing data given a particular P, so that's also a probability. I've also used the term probability when thinking about the prior, so the probability of a P, and the posterior, the probability of a particular P. Now, all of that is, the reason I make that explicit is because it can be incredibly confusing, and I think talking about things that are confusing helps us deal with them. I think that's all I want to say about that. Then once again, I've had a key concept as we only need to know the posterior up to multiplication by a constant at the moment. There are some times when you actually do need more. Now, when thinking about the coin flip, okay, so this is, so actually I'm going to write this up as well. So, if we are assuming, if we're looking in the whole world of models, which are biased coin flips, what we really want to be thinking about is the probability of a particular P given data, okay? So if we're looking at the subset of models, which are biased coin flips, we want this, and that'll be the probability of the data given P times our prior here, okay? Now, essentially, with priors, one approach is to encode as little information as possible. If you know nothing about it, okay? You know, Civia gives an example that if you get your coin from, you know, the Federal Reserve or a bank, probably pretty sure it's going to be fair. So maybe your prior will be peaked at 0.5 and have a bit of variance or spread or something like that. Whereas if you go to a casino and you expect it to be the crazy coin, which could be close to 0 or 1, maybe you want to encode that. But essentially, what we want to do is think about what our prior could be. And for the probability, for example, we know that it's going to be the probability the prior will be 0 outside 0 and 1. We definitely know that for sure, okay? So one potential prior is the uniform distribution, okay? So that's one, and we'll see some other ones, okay? So that's something that's not so informative, and we'll see there are different types of ways of quantifying information contained in priors and how we can think about that. Before we do all of that, what we're going to do is we're going to generate some coin flips and try to estimate this P, and that we're really going to be looking at the posterior of P of heads, okay? So before doing this though, what I just want to say is that the likelihood in this case, the probability of data given P, we've seen what that is. That's actually a binomial. We know how to simulate that. We're not going to simulate the binomial now. What I've given here is the analytic solution. So the probability of seeing K heads given a probability P is proportional to, I mean, there's some binomial factor, you know, N choose P, N choose C given P, or like whatever it is, right? And so it's, the likelihood will be proportional to the probability to the power of K. So this is the probability of given N tosses seeing K heads times 1 minus P to the power of, one of these is N minus K. I'm just trying to figure out which one I want to do because it will affect the code I write. So let me just look at my, yeah, it's the second one. So let's just edit that. Whoa.
Curly braces.
Yeah. Beautiful. Okay. So I'm going to set the seed within a function call, and I apologize for that. But we're all adults here. I'm going to set it to equal to 42, and if you don't know why that's the case, I don't want to talk about it. Okay. So we're going to... Yes, so we're going to sample the binomial distribution to see how many heads we get, but we're not going to use it for the likelihood because we know what the likelihood actually is, okay? So we're sampling n, given a probability, okay? Now, we're going to plot the posterior distribution, and I just want to give some sort of... I want to define what the x-axis will look like. So we're looking at the probability of heads, right? So it's going to be between 0 and 1. And I'll choose 100 points. You can choose whatever you want. The prior is going to be uniform. Oh, yeah. Thanks. The prior is going to be uniform. And I should actually define that only for 0, 1 and have it not like 0 elsewhere. But because the space we're looking at is just between 0 and 1, where we're not going to do that. And the posterior is going to be the x-axis, the probability, to the power of, it was k. So k is the number of successes, well, times 1 minus the probability, x, to the power of, it's capital N minus the number of successes, okay? And, I mean, the prior is 1 in this case, so we can kind of ignore it. I don't want you to do that, okay? I want you to multiply it by the prior, because you always want to multiply it by the prior, even if it's 1. If you don't, it's not generalizable, and you'll forget to later on, or I'll forget to. Okay, something I've also done here, because we're interested in relative probability, I've divided the posterior by the maximum so that it peaks at 1, okay? So we're going to call that, so hopefully that works. Now I want to plot posterior, and we have default values for p and n. We don't want n is equal to 0 though. I'm fine with p being 0.6, but let's just choose 10 flips. Okay, cool. So given 10 flips with probability 0.6, what we'll see is that there's a peak around 0.6, closer to 0.7, and we'll see that, you know, between 0.4 and 0.6 is kind of probable. We'll see how we'll be able to actually quantify all of these very soon. So we'll see how to say, with what percent belief can we say that the probability is greater than 0.4? We'll be able to do all of this quantitatively. But what I really want to stress for you is that we would have seen the proportion in this case is going to be given 0.7, okay? And that's all we will have got. Suddenly now we've got the distribution of possible probabilities, right? Between 0 and 1. And we can see very much how likely or what our degree of certainty that the probability is between particular values is in particular intervals, okay? Now is one of my favorite things to do, which is to use the interact widget, okay? So we're going to call interact on plot posterior, okay? Now remember, posterior is a function, plot posterior is a function of p and n. So we're going to have sliders for p and n, and I just want to tell interact what range I want there. So p is going to be between 0 and 1, and n, and with gradations of 0.01 or spacing of 0.01 because the default is 1, and we definitely don't want that. Whereas n, I'm going to allow to be, just a sec, I want an equal sign there. N is going to go between 0 and, let's say 1500. Actually, I'll make it 1000 with spacing of 1, okay? Uh-oh. So I need another bracket there. Okay. So before actually playing with this yourself, what I just want to demonstrate is that, and I apologize for not labeling my axes. I would be very disappointed if I saw someone not labeling their axes too much, this much. Having said that, we see that in the limit of 0 data, our posterior is just our prior. It's uniform, right? So let's generate one data point. Okay, wow. So now this, suddenly we've seen it shift completely. We see the probability of tails has gone to 0. Probability of heads has gone to, well, not 0, but, sorry, the probability distribution function evaluated at 0 is equal to 0, and at heads 1. So that means that first flip, we actually got a 1. So one data point with this prior doesn't tell us much. Let's go up to 2 data points. Right, so we got a tail then. Let's just keep going, and we'll slowly see, right, as we increase n. So I'm using right arrow here after clicking on one. We'll slowly see that the spread of the posterior gets smaller and smaller, okay? So I've said that in a note, that as you generate more and more data, your posterior gets narrower. You get more and more certain of your estimate, okay? So your uncertainty decreases, okay? And that is a very important takeaway from this workshop. The other thing I want to mention, and you can play around with the probability here. The other thing I want to mention is that you need more data to be certain of your estimate when the actual value is closer to 0.5. And the reason that's the case is because if, let's say the probability of heads is really close to 1 and you flip it 10 times and get 10 heads, then you're like, oh, okay, I'm pretty sure it's pretty high. Whereas if you get 5 heads and 5 tails, it still is, it isn't quite certain. And you can prove this analytically and via simulation like this. And I very much encourage everyone to develop such interactive or, you know, basic interactive plots when thinking about this type of stuff. Okay. Question?
The plot posterior function actually generates the fake data and also does the Bayes theorem, right?
Exactly. Yeah, that's a very good question, and we'll see that. So the question was, or the statement was, the plot posterior function generates the empirical data that we collect in the world and then computes the posterior. And yeah, so let's actually take a second to talk through that code one more time. I think this will be very, very helpful. So after the comment flip coins, we generate the coin flips using np.random.binomial, okay? Then, after defining our axis, we have the prior, and then we compute the posterior. And I suppose I'm going to add one more comment in here. We compute posterior given the likelihood. And that's actually very important, that given the likelihood and the analytic form. Exactly. So thank you for that question. The other thing that I want to make clear is that you will never do this in practice. What I've just done, you'll never do it. But I think for pedagogical purposes, this is very demonstrative of the relationship between prior likelihood and posterior. What you'll do is use cool stuff such as PyMC3 and probabilistic programming, which we'll get to soon, which I can't. I'm getting too excited. So I just wanted to make a point about the choice of prior. I mean, you'll hear lots of crazy stuff, all from people being like, oh, you have to choose a prior, so Bayesian methods are invalid, which is absolute bollocks, as we say in Australia. Part of our colonial history, words such as bollocks. There are so many assumptions that go into all types of statistics. If you do a frequentist test, there are so many assumptions that you're making about even the distribution of the population you're drawing from, which you don't make explicit. One of the wonderful things about Bayesian thinking is that you have to make everything explicit, including the choice of your prior. On top of that, once you choose a prior and get enough data, you can actually see that once you get enough data, that your prior does not necessarily have such an effect. Even if it does, you've made it absolutely explicit. Even in, you know, deep Bayesian circles, I don't even know, I just coined that term, deep Bayesian circles, you have like the prior wars, you know, and this is like sub dark web stuff that is, I wouldn't get involved in. Okay, so what I do want to say though is that there are a whole variety of different types of priors. There are ones that informative, that express specific, definite information about a variable. As I said before, if you get a coin from the mint, you may want to use an informative prior with a peak at 0.5. That's pretty thin. There are weakly informative priors that express partial information about a variable, such as a peak at 0.5, if we have no reason to believe it's biased, but with a larger variance. And we have uninformative priors that express no information about a variable except what we know for sure, such as knowing the probability is between 0 and 1. I want to say two things. Firstly, there's a wonderful page that we'll link to in the resources that the Stan group, essentially based out of Columbia University, I mean Gelman's group, among other people, they have a page talking about what they recommend as priors, and they, what's that? Oh yeah, okay. They definitely recommend weakly informative priors, and you can, quite strongly actually, and you can see why. The other thing I wanted to state is that from the way I've been talking about it, you might think that the uniform distribution is an uninformative prior, okay? And I'm going to show you that it isn't. It looks uninformative, but it actually is not. So I've been thinking about this question. We've all collectively been thinking about this question in terms of the probability distribution, the posterior of the probability P, right? But Eric over there, what if he's thinking about it in terms of the odds ratio, P over 1 minus P, which, you know, there's a one-to-one mapping between P and P over 1 minus P, so he's totally within his rights to think of this question in those terms, but that really throws a spanner in the works for us, because if you look at the uniform distribution on P and convert it, do a transformation of variables and convert it to a distribution on the odds ratio, it is definitively not uniform on the parameter he's chosen to think about this question by. So in fact, it isn't an uninformative prior. And the way, one way around this is using a prior called the Jeffreys prior, which I'm not going to necessarily talk about, but it's an uninformative prior that actually solves this problem. And the way you get to it is using, essentially, I think it's Fisher information, which is a way of actually quantifying the informativeness. Like, I've used terms informative, weakly informative, uninformative, and Fisher information is one way of actually making this explicit quantitatively, which there is no point doing in a workshop such as this. In the binomial coin flip case, the Jeffreys prior is given by probability of p is equal to 1 over the square root of p times 1 minus p. Now, the next exercise is to create an interactive plot like the one above, except that it has two posteriors on it, one for the uniform prior, another for the Jeffreys. And what we'll do is we'll move the slider to see that in the large data limit, both of these posteriors are going to be the same. I mean, that's just spoiled the punchline. But that's all right. So I think I was going to say you can either do that or take a break, but that's a horrible thing to say. So let's actually just take a break for 5 minutes and then get back and maybe we can write it together. And I think, and I encourage people, I don't insist, but I encourage people to not look at their screens for the time in which they break. Your brain will thank you. It's going to take 5 minutes. Yeah, but also this tool, this bar, okay, whatever, it's fine. Is that large enough? Can everyone see the code? Fantastic. All right, so for those of people who just came in, I'm not going to get you to do this yourself. I'm going to get you to copy it from the cell 5 in the solution notebook, because it will take a bit of time and there's too much other fun to be had. So I'm going to execute this, and then I'm going to do the interact again. I'm actually just going to scroll up and copy and paste my code from before. Okay. Uh-oh. Yeah, it's plot posteriors is the new function. Okay, look at this. So we've got our uniform prior, which is 1 for everything, it's uniform, and we have our Jeffreys prior, right, which is our really non-informative one, essentially, okay? Now, this is for n is equal to 0, so these are just our priors. Now, let's have a look what happens as we increase n. Okay. Oh, wow. Great, I love how the legend is just jumping around as well. Okay, look, we're already up to 45 data points, and the posteriors look relatively similar, which is a very nice sanity check. Something I would encourage you all to do, you know, at home or wherever else you like to hang out. That was weird. I had no idea where that was going and got weird. Is to play around with different priors and see how they affect it. Get some, like, don't just randomly flip coins. Get some data sets and have a look at different priors and see how they affect what you've done. And as I said before, the great thing is that you've made your prior explicit. So the assumptions of your model are entirely explicit. I had a great question during the break, which is there's another kind of objection to this choice of prior, which is not necessarily if you choose an uninformative or informative prior, but what if you actually choose an informative one that's so informative and actually so bad and wrong that it messes up your posterior completely? And we discussed that this essentially isn't a critique of Bayesian inference, it's a critique of using Bayesian inference badly, okay? And one answer, which we'll get to, Eric will talk a lot about, is something that after building your model and getting out your posterior, something called the posterior predictive check, right? Which allows you to kind of check out how well your model performed with respect to the empirical data you saw. And actually, Eric and I were sitting around today and this model was great, and then he was like, oh wait, the posterior predictive check didn't work. And we went back and saw that the prior was...
The model was specified incorrectly.
There you go. Okay, so we're able to debug it, particularly because you make your assumptions explicit, okay? So I asked the question here, what happens to the posterior as you generate more and more data? Okay. Oh, this is exciting. So now we're just going to have a little teaser, a little intro, a trailer into Bayesian parameter estimation using PyMC3. And I apologize, I haven't actually, I mean, this has been implicit, but what we've just done is parameter estimation. We've estimated the parameter P using Bayesian techniques. So there's Bayesian parameter estimation, among many other things that Bayesian inference is useful for, which we'll see. So what I want to say before we use PyMC3 is that, well done. You've learnt the basics of Bayesian model building, and the steps that you've learnt are to completely specify the model in terms of probability distributions, okay? So this includes specifying what the form of the sampling distribution of the data is, such as the binomial distribution. It's a model that allows you to talk about how the data is generated in the world. On top of that, you've specified what form describes our uncertainty around the unknown parameters, okay? And that's encoded in the prior. Now, I wrote this formulation is adapted from Chris Fonsbeck's workshop. I think it's literally stolen from Chris Fonsbeck's workshop, but I didn't want to put that in writing. I'm putting it on video. So the last step, well, the next step after specifying the model completely is calculating the posterior distribution. And we've been able to do that by hand in this simple case of flipping coins, right? But generally, your model's probably going to be pretty complex, or not as simple as a coin flip anyway. And you can't do that by hand. And a lot of very creative, very intelligent, computationally minded people have built really solid computational infrastructures to do these computations for you. PyMC3 is one example. Stan is another example. And in fact, one of the ways that PyMC3 will compute the posterior for you is MCMC, which is short for Markov chain Monte Carlo, which is essentially sampling from the posterior in order to get it. So getting a whole bunch of samples in order to see what the posterior looks like, which is analogous to NumPy's random number generator in this sense, okay? Now, I just want to, as I said, there's a third step on me, which is incredibly important, which I will not cover, but Eric will, which is posterior predictive checks, okay? At a very high level, this is making sure that your model makes sense, okay? So what you can do is, one way of thinking about it is you've got your posterior, then you can use the results to sample what the data should look like and then compare that with the actual observed data, okay? So now for the real meaty stuff, it's, we're gonna do all of this using probabilistic programming, okay? Now, if that term sounds scary, don't worry about it. I've written, there's loads about PyMC3. I don't know what that means. I think what I meant is let's do this. There's loads of cool stuff about PyMC3 and this paradigm of probabilistic programming, two of which are, the second one, as I said, it calculates the posterior for us. That's awesome. One of the most important things is that in this framework of thinking about programming and Bayesian thinking, probabilistic distributions are first-class citizens. And what I mean by that is, usually when thinking about using Python to deal with arithmetic and numbers and data sciencey and statistical stuff, you'll call X equals an array or a matrix or a data frame. These are the first-class citizens in this way of thinking about computation and programming. What we do is we assign, in probabilistic programming, we assign distributions to names. So we can have X or Y being a distribution and combine them together in order to build up our models, okay? So that abstraction is one of the most powerful, I think, computational and cognitive tools that I've encountered in this space. I actually think in terms of API elegance and development and the idea of APIs mirroring how we think about the processes cognitively, I think Keras is another great example, and also the tidyverse for anybody who is a fan of the R programming language. That's a wonderful set of APIs that kind of express computationally how you think about the underlying processes. So without further ado, we're going to use PyMC3 to build up a model estimating a click-through rate, okay? I've given a bunch of background here to be comprehensive, but we all know what a click-through rate is by now, I hope. If we don't, I haven't done my job. So what we're going to do is, before actually doing this, we're going to sample our data, generate our data one more time, okay, just for fun. I'll just do the sum. So we've got a click-through rate of 15%, and we have 15 sorry, 150 samples we're taking. So it's going to be the sum of NP random binomial, and we have, it's going to be N PA, because we're going to have a PB soon, okay? And this is called an A/B test, essentially, where you have websites that differ in some way, and you're comparing the click-through rates, okay? So we're going to execute this. Whoa. Oh, yeah. Oh, wait. No, the N is the number of samples. Ah, yes. Okay.
You don't have the size parameter for...
I don't even want a sum then. That's fine. Yeah, okay, there's no sum, because that's right. Because I'm generating the actual number, correct, thank you. Okay, so now it's time to build our probability model, okay? Now, I just want you to notice, let's think about our assumptions here. We're assuming that our model has a constant click-through rate, resulting in a click or not. And that's a biased coin flip, okay? So then the sampling distribution is binomial, and we encode the sampling distribution in the likelihood. So it's the probability of the data given the model, right? So that's going to be the binomial. Now there's a single parameter. We've got n, so there's a single other parameter p, which we're trying to estimate, that we need to describe the uncertainty around. The probability, the click-through rate, right? So we're going to use a prior, and we'll use the uniform prior for this. You can go and use whatever you'd like. But in PyMC3, all I need to do is specify uniform. You can call it, you can specify something else, and as we'll see, it's relatively straightforward. So what I'm going to do is, I'm going to use, and this is how the API works, I'm going to use a context manager. So I'm going to call with, and I'll explain this in a second, I'm going to use the model constructor from PyMC3. So remember, or I'll remind you that we imported PyMC3 as PM, so anything PM dot is the namespace, which are a great honking idea, or whatever we're told. PM dot model as model. So we're creating a model called model. I'm going to make this uppercase M. And whatever we're doing in here now is creating this model, which is referred to as model, okay? So the prior on P is going to be uniform, okay? So I'm going to do PM dot uniform, okay? So this will be the probability. And I'm going to reference it with this variable P. Now, a lot of the time you'll see this being the same as here. And that's relatively standard. I'll actually encourage you to do that, but for the time being, just to be consistent downstream, I won't. Now, we want the binomial likelihood. So we do PM binomial, right? We're going to call this Y, so we can refer to it later on. Now, how many coin flips are we doing, or how many people are coming through? The number of observations is going to be capital M. Now the probability, the P in our likelihood is this prob. So we're essentially, in the likelihood, we need to specify the uncertainty, the prior, right? And this is the prior up here. Now, remember the likelihood depends on our observations also. So we have a keyword argument called observed, which is number of successes, I think it was, yep, okay, great. Now I'm going to execute this, and that's built our model, essentially. We haven't calculated the posterior yet, but we've built our model in this context manager, okay? Now, for discussion, and maybe we can talk about this afterwards or over drinks once again, it'd be nice to know what, and you can put this in the Slack channel as well, what you actually think of the API for PyMC3, because for me, to be able to use these probability distributions as first-class citizens and abstract over everything else that's happening, it's actually a very beautiful way to interact with my computational environment. And the question is, does it reflect how we think about model building? And I have argued ad nauseum that it does. So now what we want to do is sample from this posterior. And this is where stuff gets really, really cool. So what we do is, once again in Context Manager, we sample, and under the hood, PyMC3 will be using MCMC to sample from it. And what I'm going to do is call pm.sample. Now remember, I need to specify how many samples to take, and I'm going to specify 2,000, and I'll make a small note that what Markov chain Monte Carlo needs to do is have some sort of burn-in period. So it'll start sampling to get a feel for what the space looks like, and we want to throw away those points at the end. So there's I think the default burn-in period is 500. Is that right, Eric? And that can be changed if you feel necessary. But generally, as a first approximation, trying a burn-in period of 500 followed by getting 2,000 samples, I think that's a nice place to start. I'll also ask you to put in the number of jobs equal to 1. And then I'm actually going to remove this plot and put that in the next cell. But what we're going to do here is we're going to execute this model, and it's going to start sampling, and it's going to take a bit of time. It's using something called a nut sampler, and we'll see it's doing its thing. Okay, we're done here. And now what I want to do is plot posterior. Okay, look at that. Now I love this. What we've seen is that the mean value of the posterior is 17.2. What was the initial? It was 15, okay. And what we get is 95% confidence intervals here. So we see with 95% confidence or certainty, we can say that the real value lies between like 11% and 22%. And as opposed to getting, once again, a mean and error bars, we have the entire distribution. And what I mean by that is, let's say you wanted to, let's say your manager said to you, the manager of your growth team said to you, we need a click-through rate above 14%. How certain can you be that that the click-through rate is above 14% given this experiment? So let's actually do that. We use the ref_val argument, keyword argument, and I'm going to specify 0.14, and look at this. So here, it's given a reference value, and you can tell your manager that the model developed, given the data you know, under the assumptions that you've explicitly stated, tell you that you can be 85.5% certain that the click-through rate is above 0.14, okay? Which is a really strong statement to be able to make, which the techniques that we developed or discussed earlier, such as parameter estimation, using maximum likelihood estimate and all of these types of things, won't actually give you. They'll give you the mean, and you can get out confidence intervals as well. But this is the power of actually having the entire distribution, okay? So what I'm going to get you to do now is take 10 minutes, and then I'll hand over to Eric, but take 10 minutes to have a look at the Galapagos finches data to estimate the posterior of the mean beak length, okay? So I'll just take you through what I've done here. We're going to import and subset the data. Now, once again, to specify the full probability model, you need a likelihood function for the data and priors for all unknowns, okay? Now, I'm going to tell you what all of these things are, and you're going to write them in PyMC3, okay? What is the likelihood here, okay? Let's plot the measurements below and see they look approximately Gaussian. I'm just going to do that here. They look approximate. There's some sort of tail, but it's enough for the purposes of this, Gaussian enough for the purposes of this workshop. So you'll use a normal likelihood, okay? Now, what are the unknowns in the likelihood? They're the mean, mu, and the standard deviation, sigma. And what we'll do is we'll use weakly informative priors on both. We'll use a normal prior for mu, with mean 10 and standard deviation 5, and a uniform prior for sigma bounded by 0 and 10. Now, one of the reasons we'd use a uniform prior, or sorry, a bounded prior for sigma is it's the standard deviation, right? So it's got to be greater than 0, okay? And the reason we use a Gaussian prior, there are arguments, I think, in essence, due to the central limit theorem, that if you have a lot of random processes contributing to a quantity, the population will likely be Gaussian. And mean 10, we can think 10 millimeters on average for what a finch beak may be like, and standard deviation 5 seems reasonable. Once again, we can test these assumptions later. And I think without further ado, I'll ask you to do that, and then I'll ask you to take five minutes to do that, and then I'll, maybe a bit longer, and then I'll run through the solution, and then I'll hand over to Eric. So once again, if you have blue stickies up when you're done, and red stickies if you're having challenges.
If you need a reference to what probability distributions you can call on, you can look at the PyMC3 documentation. Just as a hint, all of the distributions that Hugo had mentioned earlier on, the normal distribution would be capital N normal, pm.normal, and it's parameterized by mean and mu and SD. Uniform is capital U uniform, and it's parameterized by the lower and upper, right? And all you have to remember to do is to give each one a name, right? That's really all. That's it.
Exactly.
All right.
Oh, that's a really good question. So, Eric, the question was, what is the 95% confidence interval? And I'll state what I think it is. And if anyone wants, I think it's actually the confidence interval of all 95% confidence intervals that gives you the highest density. Yeah, I don't think it's actually centered at the mean. Is that right, Eric?
95% is just the confidence interval.
Yeah.
Sorry. Is the question in a frequentist setting?
No. What does this actually? I mean, the plot gives you 95 cents.
Okay, so
it's 95% highest possible density. I think.
So I think the correct way to label it is, where did the question come from? The correct way to label it is the 95% highest posterior density,
yeah,
which is also named the 95% credible interval. I think Bayesian stats as a field has generally avoided the confidence interval term. Right. And what this is unlike the convoluted confidence interval definition, this literally means we're 95%. We believe that with 95% probability, the true parameter is in that range. And the nice thing is, the posterior distributions don't have to be symmetric. So your posterior distributions can be skewed, they can be shaped however they want, and you can still get that 95% thing correctly. And on each side will be equal probability mass. However, you can also define it your own way. Right? If I want from 0th to 95th percentile, use numpy.percentile, and you can get those ranges out as well. Okay?
Okay, so I'm going to start filling in this code here. Recall our prior for our mean is going to be normal with mean 10 and standard deviation 5. And then we're going to have uniform bounded at 0 and 10. And here we want to specify what mu of this likelihood is, and it's going to be this mu1, and we want to specify SD as well, and that's going to be this sigma 1. And once again, the last thing we need to specify is the actual data, which is observed, which is going to be df fortis, and it's going to be b length. Okay, now we'll execute that. Great, so that's worked. Now we're going to sample and plot. So we're going to sample 2,000 and use one job.
Is that in jobs just like 6 but not like the processes?
Yeah, exactly.
So,
But why don't I wrap up and then you can discuss it when you take over. Thanks. Great. So we're going to run this now. So Eric will tell you more about the end jobs keyword argument. Okay. Great. So I'm going to enlarge this and whoa, that definitely did something. Okay. It may be slightly difficult to see. What I'm going to do, we see that it's plotted both of the parameters. I'm actually going to ask it to, I'm going to call this again below and ask it to, is it var names? Okay, great. So I'm going to ask it to plot only mu1. Okay, and we'll see the mean is 10.5, and once again we can get any information for this posterior distribution out of there, okay? So I'm going to wrap up with that. One thing I'd encourage you to do is, in this notebook, I then go through Bayesian hypothesis testing, or thinking about click-through rates and differences between the mean of different species of finches. Eric will, the mean of the length, beak length. Eric will cover similar cases in the following notebooks, but please do feel free to go through these and ping us with any questions. The best way to ask questions about this stuff is on the issue track. I mean, besides in person, is on the issue tracker on the repository as well. That's the best for me anyway. But without further ado, I'll hand over to Eric.
Okay, let's see. Sure, no problem. All right, so pulse check. How many of you feel the need for a break at this point? A few hands. And how many of you actually want to move on with like PyMC3 stuff? Okay, apologies. Majority will take over, but don't worry about the break issue. There will be an opportunity to have like as long as a break as you need during so this section that I'm going to be leading is on the use of PyMC3, and so it's intentionally divided into two big chunks. The first chunk is going to be on this parameter estimation thing, and the second chunk is going to be on how we do a little bit more advanced things like hierarchical modeling. And within each chunk, we're going to have one thing that I lecture on, and then another thing which I release the class and do on your own time during that 1 hour segment. All right, so during that period, there'll be a bit of a break period that you can, relax your brain a bit for. Okay. All right, so I would like you to open up notebook number 3. Clearly there is the student and the instructor version, so it's obvious which ones you should be opening and which ones I should be opening. However, keep in mind though, if you ever get stuck on any of the exercises, even for the notebooks that I will let you go roam on, you can always open up the instructor notebooks and take a peek at the answer. In addition to that, I will always be flashing up the answer to whatever exercise there is on the screen, or at least the meaty parts of each exercise, all right? Okay, so let's do a very brief review of what you went through. You did parameter estimation with simulation and with PyMC3. And so what PyMC3 provides is a library of statistical distributions, sampling methods, and a way of, and a lot of tooling for helping you do these model specification plus checking, all right? So PyMC3 has a really nice API, and I've come to really like it. And thankfully, I've been helping out with the PyMC3 dev team. This Friday, there'll be you may have heard some stuff about the PyMC3 computational backend. I'll address it this Friday at the tools session. But the short story is there will be a PyMC4. We're trying to preserve the PyMC3 API as much as possible for PyMC4. And the PyMC4 will be based on TensorFlow, okay? So that's sort of like long story cut short to 30 seconds. Meanwhile, let's come to notebook 3. So think about the case where you're interested in an experiment, or you've done some observations in the wild, say with Darwin's finches, and you want to know if there's a difference between 2 or more groups that you've measured, right? This is what notebook 3 is all about. Inherent behind doing this comparison of groups is the need to estimate the parameters for those groups, which we then compare. Right? Does that make sense to everybody? We want to compare 2 groups. We compare when we're comparing these 2 groups, we're really interested in comparing the key parameters of those 2 groups. So if 2 things are, say, normally distributed, or t distributed, or whatever distribution that has a mean, like a mu parameter, then really what we're interested in is comparing the posterior distributions of that mu parameters. So inherent in doing any of this comparison stuff is a parameter estimation step. What's really nice with PyMC3 is we can actually do all of this in one model block, in one code block, all right? So this is, what we're going to go through here is this, we're going to go through a simplified case. We just have 2 groups, but it generalizes to more than 2. So this is a very ubiquitous task. 80% of the, actually I think that 80% of what we'll be doing in Bayesian inference is this sort of walk in the park, commonplace comparison of this group versus that group under a particular model. Like that's really most of what we're interested in doing. Okay, so Hugo has already led you through the syntax, an introduction to the syntax for PyMC3. And so what I'm going to do with this notebook is actually give you another example of how you, which really just serves as more practice, getting your hands more comfortable with PyMC3 syntax, all right? And so what we're going to do is we're going to use this particular example, which is borrowed from a paper by John Kruschke on the effect of a drug on people's IQ. All right, so we're going to look at this data set. So I'd like you to think a little bit about how you might model this problem, right? Let's have a chat with your neighbor. Think you've already gone through the process of like describing the finches with particular probability distributions. I'd like you to chat with your neighbor. What kind of distributions might you need in looking at this particular problem? Keeping in mind that the problem setup is all inside your notebooks, right? We have our 2 groups. There's a case, there's a control, there are some measurements. Before seeing any data, what do you think would be the modeling strategy? I'd like you to chat with your neighbors about this. If you need paper, raise your hands. I'll come around and bring it to you. All right. Okay, great. Good stuff. Let's talk through this. Volunteers, what is the kind of model that you're thinking of? So given the framework that Hugo has provided you guys, there's the priors, there's the data, and the likelihood function. Then there's the posterior distribution. What we need to do as PyMC3 modelers is Bayesian modelers, we need to specify our priors and an appropriate likelihood function, right? Any volunteers? What do you guys think might be a suitable set of priors for what parameters of interest in the likelihood function? Any volunteers? It's in really small font for a reason. Any volunteers?
Will IQ function be normal?
IQ, we might choose to model it as a normal distribution, okay? And this would be the likelihood function because that is the data that we have observed, right? So we're saying, given that we've observed, so we're saying we have data on hand, we think it's normally distributed, so that is the likelihood function. What are the parameters of the normal distribution? Mean and standard deviation. Okay, great. So then what then would you think would be reasonable priors for the mean and the standard deviation respectively? So let's think about the mean. Mean might be 100 if we have like prior knowledge about the mean, okay. Would it be a fixed value or would you want to put a probability distribution over that mean? Pardon me? So you might want to say, okay, the mean IQ might be normally distributed with its own set of parameters, right? What about the standard deviation? Any volunteers? Okay, some form of a flat distribution. Are there bounds on the value of the standard deviation? Right, standard deviation cannot be negative, so we can encode this as part of the prior by picking only bounded distributions that are bounded to be greater than 0, all right? So this is sort of like so what we've done just now is essentially think about the data generating process, right? Hugo?
I might have a silly question. Can the mean be negative?
So yes, this is another really good question. Can you have negative IQ? Whoa to that person. Like we think of IQ 70 as being fairly handicapped already. What would it mean to be negative IQ, right? Like I'm not sure. So, pardon me? Brilliant. that person's negatively brilliant. We actually, in addition to thinking about IQ as being, say, so the mean IQ, we might, in fact, want to put in an alternate model specification, if we didn't do it this way already, that IQ can only be positively distributed as well, right? That's another prior that we can encode inside our model. But for the purposes of like keeping things simple for today, we're just going to think about IQ as being normally distributed, ignoring the fact that normal tails also can go to negative, like with really low probability. And we're going to think about the mu of that normal distribution as being also just a normal distribution, okay? What I have found really helpful in this Bayesian journey of my own is to be able to think of these probability distributions and how they're related in a pictorial fashion, right? So you will see these diagrams pop up all the way from notebook 3 through to notebook 8, okay? And in these diagrams, the way to interpret them is anything that's white is the likelihood function, anything that's red are priors, okay? And anything that's hyperprior, which you will see later, will be there will be an extended chart of stuff beyond one level of priors that we're encoding. Here are some of the modeling choices I've made here. First off, in this particular model that we might want to say that instead of using a normal distribution, we might want to use a t-distribution. The t-distribution is the generalization of a normal and a Cauchy distribution. So the t-distribution has this parameter called nu, which is degrees of freedom. When degrees of freedom is set to some really high number, the t-distribution looks like the normal distribution. And when the nu is set to a really low number, like 1, the t-distribution becomes the Cauchy distribution, which has really fat tails on both sides. Okay, so it's a bit more flexible of a distribution, so we might want to use it, but then that does also introduce this nuisance parameter nu that we're not we don't really care about it, but we need it for the modeling purposes. In that case, what this means is we need to put a prior distribution on nu, and since nu, from background knowledge that I have already, we know that nu is shared across the groups. It's a degree of freedom parameter. We put one prior distribution and we have that nu shared between the two t-distributions, right? Then there's a mu for the first group, and then there's a mu for the second group. And these two mu's are, we call them normally distributed. If we wanted a fairly flat normal distribution, what would you set to the mean and the standard deviation to be? Standard deviation a lot, yes, exactly. So if we were trying to be uninformative, we didn't want to say too much about what the spread of mu values could be. We could encode something like a standard deviation 100 sort of normal distribution. The mu value wouldn't really matter, because if you had that sort of level of standard deviation, well, then your variance is really high, like square of that, and so whatever your mu value is, it's just probably going to look pretty flat. The final part is the sigma, the standard deviation for the likelihood function, right? The standard deviation for the likelihood function. And in this case, the standard deviation for the likelihood function, there are two separate standard deviations that we have to specify, and they are both positive bound, so that means we can take advantage of the half Cauchy distribution. And half Cauchy doesn't have to be the only distribution you can use. You can use exponential distributions. You can use other positive bound, also fairly flat kind of distributions if you don't want to be particularly informative and you want the data to so-called speak for itself. All right? Okay, so this is sort of the generative model. And if in the course of the next few hours, you will get a few opportunities. So in the next course of the next few hours, you will get a few opportunities to talk with your neighbor, to build these, what we call data generating processes, right? And the way I think about it, there are two ways to write these models. The first way is the way we've done it. That is to say, we don't have a fully mechanistic understanding of our system. We don't know exactly how IQ is sort of generated, so we can't specify a math equation from first principles and then put priors on each of the parameters of that math equation. So instead, we go backwards, all right? So the first way is to go backwards from the data, and then we start to specify, or sorry, we go backwards from what we think the data will look like, having not seen any of the data. Then we put on the priors that we think might be most, that can encode the information that we already have, and then we write the model in PyMC3. The other way is, as I had mentioned just now, from first principles. If you have a physical system, then, well, you're in luck, right? You can write the equation for the physical system, and then you can use that equation and put on the appropriate likelihood function and the parameters for that system. We'll see an example of that towards the end, all right? Okay. I'd like you to go ahead, explore the data a little bit, run that first cell, which is a convenience function that I've built in for you. It's called load Krushki. Get a feel for what the data looks like. You should see that it has 3 columns. There's a treatment column, which indexes what treatment there is. There is the IQ of the particular participant. And because I don't want you worrying about like scikit-learn and the likes, I've already encoded for you numerically a one-hot or a numerical encoding of the treatment group that each participant has been placed in. So for example, the placebo got 1, the drug got 0. You might want to flip it around, totally fine, okay? Everybody okay with that? Thumbs if you've already loaded this cell. Okay, that's good. Go ahead, try the next few exercises below. And I'd like to have you spend about 5 minutes doing the next few exercises up to the point that you get this curve over here. And at this point, I will make a few points about this thing that we call the ECDF. All right, so go ahead and do your thing. Yeah, you probably could do that as well. All right, so I think the only choice, the modeling choices that go into this decision to use the t-distribution was really just to seek a bit more flexibility in that say, for example, we had another data set that was that had a bit more outliers, right? The normal distribution would it'd be difficult to capture those outliers with the normal distribution, and so those would influence the likelihood that is calculated inside the model, right?
So does that mean this is actually going to try to fit the degree of freedom parameter?
That's right. It will try, and you will see later that it's sort of a nuisance thing we don't care about, and it's.
That's interpretable, right? Usually you think of like the degree of freedom like the sample size.
Yep. So you could also, yes, you could totally like put a number there. But let's say there were other hidden things inside the data set, for example, that you didn't capture, and the sample size wasn't the only thing there. So
is that a thing, like to think of the degrees of freedom
as a parameter?
as something other than like sample size -1 or whatever?
Yep, absolutely. And the reference for this is John Krushki's paper. It's called BEST. It's the best method. Bayesian estimation supersedes the t-test. That's but I don't know if the acronym was intentional by John Krushki. But yeah. And I think we've referenced at the bottom of this notebook. All right. So for the rest of you blue stickies, if you have gotten to this plot, other than that, and if you've already done this part, feel free to make an attempt at implementing that pictorial model inside PyMC3 code, using PyMC3 code. Okay, so for the interest of time, let's pause for a little bit and take a look at this diagram here. In the previous few notebooks, Hugo had shown you the histogram, right? A histogram of stuff is how we're usually used to looking at distributions, both continuous and discrete. I would like to introduce a different kind of view on it, which is the ECDF. And how many of you have heard of the ECDF? Okay, good. This is a stats crowd, which means a bigger proportion, the value parameter P would be higher than in the network analysis class that I had done. the ECDF is a bit more informative than the histogram, and I would like to illustrate it by showing 4 points of things you can grab off from the ECDF that you might not easily get off from a histogram. But before I go on to that, let's talk about what the ECDF is. If you were here for the network analysis class, apologies that you're going to hear it the second time. Hopefully it's a good refresher. The ECDF plots a cumulative curve of how many data points are lower or of smaller value than a particular given value. So we take all of, say we have IQ measurements. We sort them from lowest to highest, and then on the x-axis, we plot what is the IQ value. On the y-axis, we plot the cumulative fraction of data points that are smaller than that particular value. All right? Everybody okay with this definition? Okay, good. If I were to show you a histogram of this, it might look kind of normal, right? But why would I not want to show you a histogram? It's because you can obscure stuff by changing your bin size. If you change your bin size correctly, you can obscure those outliers that your advisor didn't really want to see, right? So using the ECDF keeps us honest by using all data points inside the plot, okay? That's why it's important. Now, if I showed you the histogram, could you point out the mean? Probably, right, with relative ease. If your bins weren't too large, you could get a fairly good estimate of where the mean was. How about the median? Little harder, right? It's a little harder. On this ECDF, though, where is the median? Yeah, the median is the 50th percentile value. So if I wanted to get the median of the blue curve, literally draw a horizontal line from here to the blue curve and drop a line down, and I'll see the median of the blue curve is roughly about 100. And then the orange curve was roughly about 103, right? So we can read these off better, more easily. Let's say I wanted to ask you for the interquartile range on a histogram. Could you point that out? Even harder than the median, right? On the other hand, what's the interquartile range as read off from the ECDF? Yeah, draw a line from 0.25, drop it down onto the x-axis, draw a line from 0.75, drop it down to the x-axis, and there you go. You've got like the interquartile range. What if I wanted the arbitrary percentiles? Same old thing, right? So this is the advantage of using the ECDF over the histogram, all right? And so for this reason, I'm hoping you will use the ECDF more than you will use the histogram. The only thing that goes against the tide that makes it hard for us to use ECDFs is that most people are used to seeing histograms. That's all. But if you use ECDFs more, then more people see ECDFs, then more people will be used to ECDFs over histograms. So just start using it and people will get used to it. The mean? There isn't. The mean is technically defined as the expectation. So we really can read off medians more than we can read off the mean. Oh, sorry, I forgot. Can you read off whether there are repeat values inside a histogram? No, that's completely obscured. In an ECDF, you look for the vertical lines. And that's where the repeat values are located. Finally, in a histogram, can you find outliers easily? Maybe. But if you had the ECDF, they'll be really obvious on the curve, all right? So those are the 4 reasons why you should be using ECDFs over histograms. Now, however, there is a place for histograms. It's not like that we want to get rid of histograms. There is a place for it, and that's for, I think, the well-behaved distributions. Right? We know what the normal distribution looks like, the binomial distribution, etc. So that's a reasonable place to use this stuff. Okay. Now I'd like you to go on to, so do we have any questions before we go on? Nope? All right, now I'd like you to go try writing the model. And just as a little heads up, the model inside the instructor notebook is slightly different from the model that I had drawn in pictures. Don't worry about it, I've done both. They more or less converge to the same answer anyways, given the sample size. So you can ignore the discrepancy in the instructor notebooks with the diagram. All right, so give that a shot. I'd like you to give that, and just so that in case you ever get stuck, the skeleton code is up here. You can also look at the instructor notebooks, all right? blue stickies if you're done. Take off your blue stickies if you're still not done. And we'll aim for 50% quorum on this. Because don't worry, you will get a lot of practice with PyMC3 syntax. So some people were quite asking, this thing that we have over here for the exponential distribution in the instructor version of the notebook. So if you didn't specify it with a half Cauchy with, say, some really wide variance parameter, you might want to use instead the exponential, which in this case also has a lambda parameter that causes it to take on a large range of values, right? So if you had lambda equals 5, it would be basically exponential with lots of mass centered on point, like the mean would be, I think, 0.2 or something, given the parameterization. So this being 1 over 29, it'd be like really, really large range of new values, for example, okay? I actually would encourage you to do pm.half-Cauchy for this, right? And use beta equals 100. Right, so we can follow what's inside the diagram.
And you can just add a number.
You can. It is totally permissible to do that.
So
These are first-class objects.
why Prevalence deterministic?
Ah, okay. I will talk through that in a moment.
You can't just add
Pardon me?
you can't just add a
What do you mean?
Oh, well, for the difference in the means, you didn't just write one mean minus the other.
Okay, so I put this in pm.deterministic because we want to be able to grab it out as one of the variables for which we want to visualize the posterior distribution on. All right, so let me maybe talk through this for a little bit. Okay, so in this model specification, we have all of the priors. We have all the priors listed up here. There's hopefully enough boilerplate code or hints for you to follow along. If not, don't worry. These notebooks exist. One way that I have learned Bayesian inference is actually staring at other people's PyMC3 models and thinking about them, and then breaking the models, and then trying to figure out why they broke. All right, so this is a perfectly legitimate way of learning Bayesian inference, at least for myself. All right, so we have the priors. And then we have the likelihood functions, right? We parameterize them by student t distributions. And then we can calculate some things that we normally would be interested in, given the data, such as, for example, the effect size, right? We're interested in the effect size. And one thing that's really cool is we can do math with these probability distributions and not worry about the specifics about them, right? We can take one probability distribution, mu drug, and subtract it from another probability distribution, mu placebo, and we'll get back the proper probability distribution for those two, for this parameter called this parameter that we're deriving called the difference of means. And then the effect size is also something that we can look at over there. Now, if you were to look at this data in a frequentist mindset, you'd be looking at the point estimate, and you might say, oh yeah, there's a pretty big effect size, or moderate sized if you look downwards later. However, when we go and discuss this later, we'll raise this question of, would you really, really recommend this drug on the basis of this posterior distribution? And so one of the things that's really nice is things for which we would normally have just the point estimate. With a probabilistic programming framework, we now can get proper probability distributions over that parameter of interest.
So Eric, sorry, you may have mentioned this while I was out getting candy, but it may be worth mentioning the use of PM.deterministic.
Yeah, okay. So a deterministic, so PM.deterministic refers to this being a deterministic transform between the variables. It means we're doing math with them. And the only reason why we put them inside the PM.deterministic thing is because we might want to visualize them later, right? So that's the reason why we put it inside PM.deterministic.
Somebody is creating like a creative member of something that's like in the IMC land called diff.
That's right. And this itself is a distribution. Right, so it's just it's merely a deterministic transform on distribution objects, which yields another probability distribution.
Oh, so it's like pointwise.
It's not exactly pointwise. So this is where the abstraction with PyMC3 comes in really handy. We don't have to worry about it. The technical thing is, if I remember correctly, one of addition or multiplication is a convolution of two distributions, and like, my gosh, that's just it's a lot to think about. On the other hand, if you had to multiply or divide, literally, we have that over here. We have a division over here that we don't have to worry about how to do this convolution operation. All right?
Another way to think of it is that when a deterministic variable is assigned like that, it depends deterministically on the parent values. So there's no, it doesn't depend probabilistically on them. You don't need a prior, anything like that.
Hugo, you should repeat that.
Yeah. So one other thing is that PM deterministic assigns to a value something that depends deterministically on its parent value. So how you're assigning it. There's no probabilistic association between these variables and that. You can write out the equation. Of course, you get, because these have a distribution associated with them, you get a distribution here as well.
All right, are we cool with that?
Minor question, but you're dividing by 2, is that integers?
Pardon me?
Is there a reason only one of those items is divided by 2?
Oh, I might have gotten the math wrong. This divide by 2 has to be outside, right? Yeah. Okay, cool. We'll fix that. All right, so that means if I got the math wrong, you can't really interpret the effect size plot there, which is why we need peer code review for data scientists, right? Data scientists need code review. Thank you very much. Okie dokes. So we'll ignore the effect size thing, but I'll get to you in a moment. We'll ignore the effect size thing later on, but I just wanted to make the point. You can, instead of just getting a point estimate for the effect size, you can also get a probability distribution. All right, question over there.
Oh, so you mentioned that like the distribution should be bounded between 0 to 100. Where does that shown in the...
So if you use the beta distribution, for example, beta half Cauchy distribution for the standard deviation, the half Cauchy distribution is already bounded above 0. It is literally chopping the full Cauchy distribution in half at 0. So beta equals 100 doesn't mean that the upper bound is 100. It means the standard deviation-like parameter that controls how wide this Cauchy distribution, it's parameterized by basically a really large number. All right? Okay, so how are we doing with that? You can then, as Hugo wrote in the other notebooks, bust out the sampler. If you are Thomas Wiki, you would call this hitting the inference button, right? And he has a trademark apparently on that button. And it's really what probabilistic programming is doing is saving you from doing a lot of hard in calculus, all right? Writing all of these models in math would have been crazy. And doing all the integrals would have been crazy. But with probabilistic programming, we've abstracted that all away. And now we can sample from what the posterior distribution would look like. And if you do this thing over here, plot posterior, you should get something like that. So go ahead, go to that, and blue stickies down. And then put them back up when you hit this plot posterior thing.
What should we do if we get errors about acceptance?
If you get errors about acceptance, I don't want to talk about it right now. I'll sweep it under the rug for this tutorial. It is a real thing. As I was building this, the notebooks, frequently I would hit this acceptance thing. You have to do things like either reparameterizing the model, so respecifying the model, or increasing the number of burn-in steps before you do the actual sampling, Hugo. And the third thing would be to change the there's this changing of acceptance probability parameter that you can specify for the MCMC sampler. For the time being, I don't want to bring those in because those fall under like things you will do later on. All right, so blue sticky up on your laptop if you have reached this point, the plot posterior. Also, keep in mind if you're getting errors about this parallel processing sort of thing, remember to specify n jobs equals 1 so that you don't get this error. Okay. In the interest of time, I'm going to show you the completed work. As mentioned earlier, you can take a look at this notebook on your own time. Like I mentioned, one way of learning Bayesian stats is by looking at other people's models and trying to reverse engineer the generative model that they were thinking about, all right, and figuring out what the modeling assumptions are. So you should get, if you look at the posterior distribution plots, they should look something like this. Hugo has already shown you how to interpret these posterior distribution plots. So for example, the mu for the drug-treated participants was at, is centered around 102, IQ 102. It's 95% highest posterior density, ranges from 101 to 104. And this being a thing where we've modeled it with a normal-like distribution means we get a distribution that is fairly symmetric around that. It looks like a bit like a normal distribution itself. Likewise for the placebo, all right? So Hugo left off at this thing called Bayesian, so-called Bayesian hypothesis testing. A lot of you might be wondering, like, okay, the frequentists have a hypothesis testing framework. Is there an analogous thing in a Bayesian setting? My response would be, don't ever do binary decisions, right? Don't do binary decisions. Unfortunately, some people still do think in binary ways, so we have to find a way to bridge it over for them. And this is where this Bayesian hypothesis testing thing can come in handy. If you looked earlier on, we defined this thing called the difference of means. If you think back to what the t-test is trying to do, it's essentially testing whether the difference of means is 0 or not. If the difference of means is not 0, then we think we have some so-called statistically significant difference, right? If the difference of means, the so-called confidence interval, encompasses 0, then we can't make any inference. We are unable to reject the null hypothesis, right? Like, you can never accept the alternate hypothesis, which sort of doesn't make sense to me. In this setting over here, we again have, because of the deterministic transforms, we are allowed to have a posterior distribution over the difference of means. And in this case, the difference of means goes from 0.573 to 4.607, right? So those are what we believe is the difference of means, having seen the data, right? Given our prior distributions that we've imposed on the model. Does this make sense to everybody? This is sort of okay? You get this posterior distribution over that. And we can ask the analogous question, except with a little bit of a kink, all right? My question would be, for what practical purposes would you consider a range equivalent to 0? A difference of IQ. Is the difference of IQ range from -1 to +1 equivalent to 0? Or is the difference, do you really have to have like a range of -0.01 to +0.01 for this to be 0? A priori, what would you decide is a region of practical equivalence to the value 0? What do you guys think? What do you all think? Does 5 points of IQ matter? Not really. So one region of practical equivalence that we might set would be -2.5 to +2.5 IQ points. That difference, if anything falls within that region, that's equivalent to 0, right? That's equivalent to saying there is really no practical difference between them. Might we say, so we might want to, so a priori we have to define, oh yeah, we have this region of practical equivalence. So -0.25 to +2.5 is our so-called region of practical equivalence. And if you were to plot this on the difference of means plot, that region of practical equivalence, a rope, literally, bounds a region that we think is equivalent to 0. And this 95% HPD actually overlaps with that particular rope. So what would we conclude here? Could we so-called reject the null? If you're a frequentist, yeah, but if you were really considering the problem correctly, sorry, I had to say that. If you were really considering the problem correctly, you would be thinking, yeah, our differences are really not practically useful, right? These differences that we're observing, they're not practically relevant to the problem at hand. And therefore, we wouldn't even be interested in this binary decision of, yeah, we reject the null, don't reject the null, publish this paper or file it in the drawer, right? We don't do that. We say here, we don't have enough evidence to conclude, right? And it could be that given the evidence at hand, given infinite data, we might still never be able to conclude that this drug was ever useful, right? So that is one aspect that I want you to consider. If I had done the effect size calculations correctly, apologies that I didn't, but if I had done it correctly, we would have observed a posterior distribution on the effect size. Now, if we know what effect sizes are, and let's just assume for a moment that this effect size is correct, if we knew what the effect sizes, common effect size ranges were, something of less than 0.2 is considered small, 0.2 to 0.6 is approximately considered medium effect, something greater than 0.8 is considered high effect, and look at the range for this effect size HPD. It is 0.092 to 0.822. We practically have no information to decide whether this thing had any effect or not, had a small effect or a large effect. So again, practically speaking, we can't make a decision off of this data set, right? We can't say whether this drug actually had a big effect or a small effect. It could be anything, right? Okay. We could say it probably had a small effect. Someone could come back and say, yeah, but it also probably had a big effect. And then another person would, but yeah, the majority mass is like a medium effect. And we could do something like that, but then think about it. Let's put this down for a little bit. If you were to just look at the difference of means, if you were just to look at this difference of means, would you recommend that this drug be recommended for some treatment of people? Like, would this be a super drug that you would go, if you were the FDA, would you want this on the market, really?
Are there any side effects?
No side effects. Assuming no side effects. Thank you. Yes, I should know this. I work for a company that deals with this.
Is it cheap?
That's another question we can ask. But let's think about the scientific data at the moment. It's a lifestyle drug? No. Would this be something, would the claim that this improves IQ be scientifically supported?
That sounds like a bulk illegal.
Pardon me?
That sounds like a bulk.
Yeah, probably. Let's look at the data. In my opinion, this claim would be fairly unfounded, right? There would be poor evidence in favor of this claim. There's no practical difference. We already agreed. 2.5, an IQ range of 5 plus minus 2.5 for differences doesn't have any particular practical significance, for lack of a better word. Okay. Now let's go back to this thing that I wanted some of you who might have already done this, that I wanted you to take a look at. This is what we call the model checking step of inference, of Bayesian inference. That is to say, if our model was specified correctly, we should actually get a posterior distribution. So if our model was specified correctly, then what we have on hand is a data generative model. Let me swipe back up to here. If our model was specified correctly, then we should be able to forward simulate from this model and recover a distribution of samples from this model that looks a lot like the data we generated on hand, right? So now this of course raises the question, there may be multiple models that generate the same data set. We won't argue about that. That probably means there are multiple equivalent models. For the time being, let's just focus on this one, right? If the model is correctly specified, then the data that we draw from here should look pretty close to the model, to the actual data that we've collected. So what do we mean by forward simulation? Literally, it looks like this. I draw a normal, I draw a mu, I draw a mu, I draw a half Cauchy, I draw an exponential according to the correct probabilities. I just run it through the model and parameterize the two t distributions and then draw a value from the t distribution. That's all we're doing, right? We're forward simulating given this model at hand. If we've estimated the parameters correctly, this t distribution, the values generated from the t distribution should look at the data. And so that's what this thing called the posterior predictive check is all about, right? So what we're doing with a posterior predictive check is we're sampling from the model, that is this line over here, sample equals pm.sample ppc, right? So we specify the model, we specify how many samples we want, and then we specify the particular trace object that we had sampled, that was the result of sampling. We specify that, that we want the PPC samples. And then we do a check of the distribution of the posterior distribution samples against the data. There are multiple ways to do it. The first way you should be doing, which is the way I want to introduce here, is to simply look at it. Do the eCDF of the data look like the CDF of the posterior distribution? And if they line up closely, then you have a good model. And if they don't line up closely, as I've seen in a few models that I've implemented myself, then you have a model that is misspecified, and it is not describing the generative process for the data on hand, right? People okay with that?
What's your boundary layer?
Pardon me?
What's your boundary layer between comfortable and not?
Get as close to the truth as possible. And so if you read Mike Betancourt's blogs or his website and some of his papers that he's written, model building is not a one-time process. Model building is iterative. And last night when Hugo and I were like still working on, this morning, sorry, when Hugo and I were still working on some extra stuff, I was building this model for the Darwin's finches data set and finding that the model was misspecified, so I went back and I respecified a new model that I thought described the data generating process and found that that still didn't describe what I wanted. So I built it 2 more times before I finally reached a model that was correctly specifying, or at least one model that was correctly specifying the data generative process. And it turned out it was the simple model that was correct, or was one of the correct models, right? I tried to build it from first principles. That didn't really work, so I did the backward approach in the end, and that turned out to be a correct approach, right? So it's an iterative process. You don't build one and then say that's it. You build one, you critique it, you go build it again, you critique it again, you build a third one, you critique it until you get as close as you can to ground truth, given the data. So I don't really have a boundary layer. I just have many, many rounds of iteration, all right? Yes, you can calculate like the KL divergence of these two things, for example, if you wanted to. Right, totally okay.
If you iterate that much, at some point you feel like you're overfitting.
You probably could. Yeah, yep, you probably would be overfitting especially if you built these really complicated tons of parameter models, which we know neural networks are, right? So deep learning is a thing that is prone to overfitting. And so if you are at the point where you've caught yourself building these complicated models with lots of parameters, then yes, you might overfit. That's one check. The other check, so one check is look for model complexity of some sort. Like the other check is, do you have new data? If your model is describing the generative process for that class of data correctly, on new unseen data, your model should make PPC samples that look like the new data, basically. You probably could as well. Exactly. Well, of course, that means we would be building a model conditioned on smaller amounts of data, which is always a problem, right? Okay?
Maybe it's a stupid question, but what are the parameters that are being trained? I think that didn't help us.
Okay. So in this particular model, the parameters that we are fitting are each of these prior distributions, essentially. Right, so we're saying over here in this model up here, right, sigma, mu, and nu are the parameters that we're trying to fit to the data. However, instead of specifying and optimizing a single value, I want to capture the uncertainty surrounding the mu. So instead of specifying that I start with a particular mu and then shift that mu around, I start with a probability distribution over mu and try to capture the probability distribution of mu that best describes, that best fits the data. So you can think of it as sort of like shifting your distribution around, or shifting basically shifting the distribution around. That's the easiest way to think about it. Right? Shift the distribution around until it fits the data with the appropriate uncertainty inside there as well. All right, people okay with that? All right. Empirical Bayes, so I heard, was look at the data, then set your priors. Empirical Bayes, as far as I've heard, is look at the data, then set your priors. Is that right? Is that what you're thinking of?
You estimate the hyperparameters from the marginal distribution.
Pardon me?
You estimate the hyperparameters from the marginal distribution of data.
Yeah, so you look out.
Theta and mu.
Yeah.
Hyperparameters of prior distribution.
Yeah, which is equivalent, like I have to look at the data first before yeah. So I haven't compared it here. Yep, it could perform well. It could also lead to, so we still have to do this iterative model building thing. You just can't escape from it. There isn't the master model that will describe your problem. How are we doing? Okay, we're not doing so well with time, but that's okay. There are a lot of good questions that were being raised, and I'm very appreciative of that, okay? So, in the interest of time, rather than have the class do this first, let go and like build a model for Darwin's finches, I'm going to move straight on to this other, I'm going to show you the conclusion for Darwin's finches, and then use that as a way of motivating the next section, which is on hierarchical modeling. Are we okay with that? Cool with that? Okay, cool. So, to show you the conclusion on that, I would like you to open up the instructor version of notebook number 5. And you don't have to run anything. I will go through just a few major points that I wanted to highlight through the exercise of notebook 4 and notebook 5. One being, the first one being, if you observed how we specified that model, that was a lot of lines of code. One distribution per group, and then like that sort of thing, right? So imagine if you had like 20 groups and you needed to do a posterior estimate of those groups' mu's. Like you would write a lot of pm.normals, pm.studentt, right? You can take advantage of NumPy's fancy indexing, NumPy-like fancy indexing, which Theano provides to very concisely specify a model. So that exact same model that we wrote earlier on can actually be specified in 1, 2, 3, 4 distributions, right? Taking advantage of this shape keyword argument. Now, this shape keyword argument can get a little confusing, so I always find it useful to draw it out for myself first. I'm saying that I have 3 t distributions. They each have a mu and a sigma, 1 through k, 1, 2, and 3, and each of these mu's are there's a corresponding mu that is drawn from one half normal, another independent half normal, and a third independent half normal. People okay with that? So there's fancy indexing that you can use inside the prior distributions, inside the likelihood distribution as well. So just wanted to put that out there, all right? That was one main point that I wanted to show. The second main point that I wanted to show is if we assume a model that's like this, that is to say, I put one prior for the mu, and then for each mu, I have one normal distribution. For each sigma, I have one normal distribution. And let's say I observe, some of you might have noticed in the notebooks, I observed this unknown species of finch for which I only have one sample. If you were a frequentist, you would find that that would be the only, you couldn't make any statements about the uncertainty surrounding that species, say finch beak length or finch beak depth, right? With only one sample, you couldn't make any statements about that. With a Bayesian approach, now I just want to put this out there, with a Bayesian approach, you can still get absurd estimates of this, of the posterior distribution. So think about it. Given what you know in biology, given a single observation, the posterior distribution for this unknown species is for beak length, ranges from 0.019 to 125 millimeters. Does this sound reasonable to you? Reason being, sorry, so let's do someone from this section. Pardon me? That is really high uncertainty, yes, and we don't reasonably expect like a finch beak to really be close to 0 in millimeter length, right? And this is exactly what this posterior distribution is describing to us. Any other reasons why? Oh yeah, a beak that's like 125 millimeters long is 12 centimeters. Like a finch is this small, and it's got this extremely long beak, right? All right, so that again is an unreasonable or an absurd estimate given what we know about biology. So what else could there be? Right. So just now the guy who was wearing the Tesla jacket here was saying we think of IQ as being normally distributed, so biological properties we tend to think of as being as following some form of a bell-shaped curve, right? It doesn't necessarily have to be normal. It could be student T, it could be Cauchy, whatever you want, but we don't tend to think of biological properties as following this type of exponential-like distribution, right? Any other things you can think of? I can't. So, okay, we'll move on with that, right? So when we impose these independent priors on, yes?
Did you say why your model came out like that?
Yeah, so the reason was because we're imposing independent priors on each group. That is, we're saying that each group looks as it is. And if I start with the same set of priors for each group, then I let that data speak for itself, then the posterior distribution will look like that for that thing that only has one sample. And maybe if we collected like 40 more finch beak measurements, we'd be able to say something a bit more reasonable. But let's say, pretend for a moment, this is a rare new species. You really only have like a few samples that you're able to observe. When we still have this desire to characterize this new species properly, right? So how would we go about that? What do people think?
We would assume that it looks like other finches.
Okay, so, and is that a biologically reasonable assumption to make?
If we're calling it a finch.
If we're calling it a, so if it quacks like a duck and it looks like a duck and we have duck arrays and yeah, okay, I see, yeah, okay. So that's one. I think any other reasons you can think of? Any biologists in the crowd? Wow, we don't have a biologist in the crowd?
Sorry, I didn't hear what the answer was exactly, but I think it depends on what claim you're trying to make about your new species of finch, right?
Okay.
If the claim is, my species of finch has super extra special beak properties compared to other two species, then maybe no, don't use, say, distributions from you that you use that data for, right?
Sure, but then what distribution would we have to use? And that's a matter of debate. Okay, so if you're a biologist, one thing that you would think of is this idea of common descent, right? And so for this reason, we're able to justify saying that, yeah, we should look at the other finches species that are around, and maybe somehow those other finch species can inform what we're trying to estimate with this little bit of data that we have. Even if we had 2 or 3 samples, our posterior distributions would still look absurd, right? So that is what notebook 7 is going to talk about. So I'd like you to open up notebook 7. So this notebook was designed to be, supposed to be one of those exercise notebooks that I wanted you all to go and explore on your own, but we're going to do it as a guided walkthrough instead in the interest of time. Okay, so let's do that. So let's start with the data on hand. So if you could run the first few cells, you have some data, and observe again that you have 121 measurements of the first species, Fortis, 127 measurements of that Scandens species, and you only have 1 measurement of that unknown new species, which makes sense why our standard deviation is not a number, all right? So the thing that I really wanted to introduce to you is this notion of a hierarchical model. Right? And so this hierarchical model, in this hierarchical model, what we're trying to do here is we're trying to impose a model structure that encodes our assumptions. Keep in mind, we're making assumptions all the way down. We're proposing a model structure that encodes our assumptions that somehow these finch species are related to one another. All right? So let's look at what this looks like pictorially. We can say, for example, that we can preserve the bottom half of, bottom portion of the original model, where we have our individual likelihoods for the data. We still preserve the fact that we have a shared nu. We preserve the fact that we have 3 mu's that we need to estimate, and we preserve the fact that we have 3 sigmas to estimate as well. People okay with that? Okay with that? What's different is each of these prior distributions itself has a parameter of interest that we can claim, we're asserting this, we can claim with justification, external qualitative justification, that it's all drawn from one parental parameter distribution. How are we doing with that idea? Does that sound confusing? Yeah, a little bit. Okay. So what we're saying is that the generative story is this. The population as a whole has this parental distribution that governs the parameters for each particular group. Okay? I think a good example is in baseball, right? So baseball batting average is literally you're estimating the parameter, you're estimating how likely are you to hit a ball that's pitched at you. So with what we can assume is that humans on general will perform at or professional baseball players, not humans, professional baseball players will perform at some general batting average, but that individual players draw their batting average from this general population distribution. And in doing so, we have a constrained region for which this parameter can be drawn from. So likewise, when we say that with the finch beaks, each distribution, likewise when we say that each species of finch has this mu and this sigma that is drawn from a parental distribution, a population thing that governs all finches, that's what we're encoding. So when we do the maximum likelihood estimate for baseball players, and we say that this player came up at bat one time and didn't hit, do we really believe that that player's posterior distribution is like, that player sucks? No, right? Do we also believe that a superstar is made out of 5 bats, 5 hits? No, right? There is some constraint that we need to impose qualitatively by imposing this model structure on top. Likewise, we can do the same with the parameters of any model that any group, sort of group estimation model that we're writing, okay? How's that for clarity? Are people a bit clearer about this idea now? Yeah? Okay, so on the basis of this, let's move on. I feel like I need to make a decision as to whether to make this an exercise or to move on talking. Let's see, questions?
Why not have various parameters for mu? Like, why have like a single?
This one trips me up all the time.
Because you count advantage, but no, you have a likelihood per group, right?
I have a likelihood per group, but then the degrees of freedom are shared across all of our measurements. There's this weird thing that I have to discuss with you later. All right. Anything else? Okay, so I'm hesitating on how to do this. Hugo, do you have any advice for me at this point?
I would ask people,
okay, poll the class.
What would you find most valuable in this group of learners?
Okay, all right, so.
And then do the opposite.
Okay, so the intent behind the exercise, again, is for you to get familiar with PyMC3 syntax and specifying distributions, but because we skipped out on the fancy indexing exercise, I'm a little hesitant to have you do it. People okay with that premise? So if you are okay with that premise, then I'll move on as if this was like a guided, talked through lecture. And hopefully we'll be able to go through the end of this, all right? Again, my apologies, time didn't control it well just now, but this is the reality we're dealing with. So talking through a little bit of the code, basically the idea here is we can specify one likelihood, right? We can specify one likelihood. The priors are all shown here. And if you look at the literature, there will be this thing that we call the hyperpriors. The hyperpriors are the priors of the priors. If you really wanted to, you could have hyperpriors, hypercube priors. Like it could go priors all the way up, not turtles all the way down. But really, the more important part is you go hyperpriors, that's good enough for this hierarchical estimation model. All right, people okay with that? So if we want the data so-called to speak for itself, we could put, again, fairly uninformative priors. Again, this is a thing that we can debate. Then we do this mean, SD, and nu, which are the prior distributions for the student t parameter, and then we specify the likelihood. All right, that's what's going on down there. Then we have this beak depth model thing where we're sampling from it, and then that's where some of these issues that some of you might have observed, this acceptance probability thing, again, I don't want to go through it at this point, but it will show up. These are part of these model diagnostics that PyMC3 provides. And these model diagnostics are very well documented on the PyMC documentation. So I'd really encourage you to read through them to get a feel for what they're trying to warn you against what's going on over there. Finally, we can look at the posterior distribution over the beak lengths. Now for the actual, or this is beak length or beak depth? I think this is beak depth. So this is beak depth. So we can look at the posterior distributions for beak depth. You will get something analogous for beak length. And take a look. I'd like you to pay most attention to this unknown species, right? Compare it to what you remember from before. Does this distribution look a little bit more reasonable than maybe what you had seen before? Okay, so tell me why. What makes you think so? Yeah, well, we still do have like a highest posterior density at like 0.389, right? But it's not like 0.00 something, right? Okay, so we have somewhat of a constrained posterior distribution on the basis of this one observation. Still quite uninformative, right? This is still fairly wide.
It's still a sample size of 1.
It is it's exactly that. It's Yep. Yeah, yep, exactly. So the decision we might make on the basis of this posterior distribution is go hunt for another unknown, right? And see what that beak measurement is. Anything else? What about the shape? Shape looks a bit more symmetrical, so it does look a little bit more reasonable. So let's discuss this for a little bit. This hierarchical model was a thing that we imposed on the modeling activity. Is it justified?
Probably like a domain question.
This is a domain question. So, pardon me?
Why do you think it's a finch?
Okay, all right. So we can question the underlying assumption of all of this modeling activity, that this is a finch that we're measuring. What else? And so if this was not a finch that we had measured, would it be reasonable to include it with this group population prior inside there? Yeah. So scale matters in the data, but more importantly, we're not really able, and I had saw this thing on Twitter from Mike Betancourt again. Very rarely will you be able to use a mathematical procedure to definitively say my model is correct. One, because of George Box's statement that all models are wrong, but some are useful, right? So any probabilistic model that we were writing is going to have elements that don't correspond with reality, but it can be useful. So that's one part. Two, everything that we had used to justify this model structure did not come from assumptions that were inherent inside the data. Everything that we had previously talked about to justify this model structure came from domain knowledge, external assumptions that we actually still have to go and qualitatively or quantitatively go and verify. There is no free lunch. You have to describe your assumptions explicitly and encode them in the model structure or in the probability distributions that you use. There is no free lunch, right? I just want to get that hammered home. The reason why p-values have proliferated is because academics and other people outside of the academic ivory tower have treated the t-test as the free lunch to like objectivity, but that is not the case, right? There is no free lunch. If we encode a model with this particular structure, we have to justify why we've done so. And we need external things that are extrinsic to the data to be able to justify that, right? I wanted to hammer that home.
So from maybe a very simple point of view, in this case, since we don't have a lot of data for this third, third
unknown.
You know, the thing we're probably interested in are in the two systems that we already know about.
Fortis and Scandens, right?
Yeah, and so if we compare, like, did those two change with this more complicated model? Did we gain anything from the hierarchical model for those systems?
So can someone open up the previous notebook and look at the posterior distribution estimates for Fortis and Scandens under the assumption of like independent, non-grouped priors? Can someone open that, right? And tell me what the Fortis, I think we did beak length in the previous notebook. So I have both beak length and beak depth here. So let's look at what the posterior distributions say for that. So for the beak, for which one? Fortis, 10.5 mean, okay. Under this hierarchical model, it's 10.48 mean. So in the large, so-called larger data regime, things sort of converge, as Hugo showed, with different priors. The uniform and the Jeffreys prior really converge at large data regimes, right? So the thing that was the same for all practical purposes were these two populations for which we had lots of data.
So then can we conclude that the more complicated model is the worst model then in this case?
Not, I don't know. So what do you mean by that? Well, how would you say that the more complicated was the worst one?
If we're ending up with similar distributions with the more complicated model versus the less complicated model, I would be leaning towards the less complicated model.
Sure, I would too. If we didn't have the unknown species inside there for which we had something interesting, we wanted to characterize something about it. So in the case where we didn't have this one data, one observation thing, and in this large data regime, indeed, the non-hierarchical model was the simpler model, and we might want to apply Occam's razor. Then again, we have to justify, why would we want to apply Occam's razor, right? If in this case, we have good biological reason to impose this hierarchical prior, maybe using the hierarchical model structure might have been better. So again, no free lunch. We either justify why we want to use Occam's razor, or we justify with biology why we use the hierarchical model. All right? Are we okay with this? Okay. It's this weak constraint because of the priors that I've put on this hierarchical, the hyperparameters that we've put there.
But the more hyper you go, it's weaker. Right?
Yes. It gets weaker and weaker and weaker. And you are also complicating the model. Right? Yeah, exactly.
But I guess just because you went hierarchical, that doesn't mean you're constraining the model. It's like a turtleneck spreader. It's a weak constraint, right?
Yeah.
It always seems even more constrained. Like before you had a hierarchical model, you said that it's around standards.
Yeah, yeah.
You were saying all finches are around.
Yeah, basically.
The definition of complicated. Computationally, it's more complicated.
Yep, and in terms of the number of distributions we're using.
Speaking, it seems to me that it's saying that there's a relationship is as valid as saying there's no relationship.
Yeah, okay.
So it's only computationally more complex.
Okay.
From a prior standpoint, you're saying, I'm not saying the standard deviation is 200, I'm saying it's from this distribution.
Yeah.
Which is even weaker than saying that it's a single point number, right?
That is, yep,
So
okay.
By going hyper, I'm actually
I'm relaxing the constraints that I'm putting on the model, but I'm introducing more model parameters paradoxically.
yeah. True,
Yeah. Okay, so this is great. This sort of, I'll get to you. This sort of discussion is the exact kind of discussion that has to happen between scientists. If this is not happening, you're operating in a bubble, right? And this is not what you want to be doing as a scientist.
So in terms of information, like if you just did like a normal information theory, hypothetically you're adding information, but you're also losing information by adding a parameter, but you're adding an assumption in the form of information into this, right?
Yeah.
You're kind of at a mix, right?
Yeah.
The quality of information you add to it, right?
Yeah.
You're trying to do an AIC score on the model or something.
Right. I have to think about that. I'm angling to move on to this final thing that I was really excited about on the plane ride here to Austin. But yes, I'm happy to talk with you about this afterwards, say at the Nthought reception or something like that. All right. Okay. So really wanted to drive home this idea of hierarchical modeling for you, right? Again, source code is all provided. So if you ever get stuck on hierarchical modeling, you have this tutorial's resources, I have another repository that's out there, and more importantly, PyMC3 Docs has this gallery of examples that's really, really useful. It is perfectly normal to stare at someone else's source code to learn what they're trying to learn the deeper theory. If you have talked with Alan Downey before, the API is the lesson, right? The API is the lesson. And the API introduces the high-level concept that anybody can dig down deeper if they wanted to, right? So in this case, the API is at the level of thinking in terms of probability distributions and describing your data generative story using probability distributions. That's really the big lesson that's over here, okay? Okay, let's conclude with this final thing from notebook number 8. This was the thing that I was really excited that I wanted to share with everybody. How many of you have done linear regression? How many of you have fit an IC50? Okay. How many of you have measured the radioactive decay constant of an unknown radioactive material? Okay, I guess nobody, but how about a known one? Physics class, high school, right? Or a university undergrad physics class. Okay. On my way, oh yeah, how many of you have done deep learning? Okay, on my way to Boston, I came to the realization that they are all and one, they are all the same. They are all glorified curve fitting. Right, that's all this is, right? And I want to use this notebook to show you how you can do all this glorified curve fitting in a Bayesian setting. Now, normally, we would pick the linear regression case. But I think the linear regression case is like you're fitting a straight curve, fitting a line. So it's kind of uninteresting. So let's actually fit a curve and drive home the fact that you can do math inside PyMC3 models which describe the curve that you are trying to fit. All right, that's all I want to drive home with this notebook. So I talked about an unknown radioactive material that you're trying to measure. That's the premise of this notebook. We have noisy, somewhat noisy measurements of how this particular material, Hugo was calling this very James Bond-esque, that you have this unknown material, it's got some half-life and you want to measure it so that you are able to characterize what it is and then maybe properly dispose of it, right? So let's say you're hazmat or something. So we have this curve. This is the data. This is what we've observed. And you can see it's kind of noisy, right? People okay with that? This is the most important figure from Notebook 8. This is the most important figure. It's also the only figure that I drew. So when we have an exponential decay curve, or when we have a decay curve for a particular model, for a particular, for radioactive things, we can write this equation down. It's a times e to the negative x over tau plus a c term. You know, that's like the parametric form of the equation that we can probably go and fit to the data. In physics class, you probably ran some numbers with, say, MATLAB or something, and it gave you one number for tau, given the data, right? This was so-called the maximum likelihood estimator on that curve fit. Think about this. This equation has 3 parameters. It has a, tau, and c, right? Make sense? Also, if we're trying to, now the thing about this curve is we might observe that this noisiness comes from, we might assume, for example, that this noisiness comes from a normal distribution. It's a common assumption to make, that noise is Gaussian in nature. So what we would say is that the observed value is this functional transform of the parameters with the data x plus some Gaussian noise around it. All right, and so we use a normal distribution to model the fact that we have some Gaussian noise around the observed values that we have. Okay, everybody okay with this? Here's what this model looks like in PyMC3 code. The most important thing that you need to look at is this one line over there. This one line describes the mathematical relationship between all of my 3 priors and the data. And with this so-called link function, and we usually hear link function in the so-called logistic regression case, right? So you have a logistic function as your link function. Think about it. Any function can be the link function. It does not have to just be the logistic function. So you can write this link function that looks like that, and then say that the output follows a normal distribution in which the mu is described by the link, the SD is by this prior on the standard deviation, and that the observed values are what you're conditioning your model on. Does this make sense to everybody? So if anything, that is the one thing I want you to look at for this, from this particular notebook. And like I said, any math function can be your link function, right? So what does it mean? If we scroll all the way down, you can fit exponential decay curves, you can fit sine curves, you can fit the linear regression straight line, the logistic regression logistic curve, you can fit a 4-parameter IC50, you can fit a deep learning arbitrary curve inside there, and there's this example of Bayesian deep learning in the PyMC3 docs, right? You can fit any math function, and that math function is your link function between your input data and your outputs. And this is the thing that hit me at the speed of Tesla's Roadster in space while I was flying over from Boston to Austin. And I was like, gosh, this, like, why do we divide fields by, like, there's this IC50 parameterization. It's never called a link function. This exponential decay curve is never called a link function. The only link function that we learn about in statistics class is this logistic math curve, for example. So they're all really one thing, and right? And as long as you can write the parametric form for your equation that links the input to the output, you've got a link function. And this is possible in PyMC3.
So, I'm sorry if I was mistakes, but why is it that your link function is the mean? Like, why is the likelihood normal, and why is the link function?
We encode that we believe that there's Gaussian noise around the data, and that's why we have a normal distribution conditioned on this link function and the data and the parameters inside there. All right? Exactly. Exactly, exactly. Okay, any other questions about this?
If your model is not very good, if your link function is not very good, how does that show up when you do something like this?
Your posterior predictive checks will look off because the transform on the input data will be off. And I've actually encountered this at work where things that I thought were exponential decay turned out to have more like an elbow curve. And so the exponential decay curve sort of missed that. And so, yeah, so I had to go back and rewrite that model.
You could plug in a Taylor or Maclaurin series.
Probably so, yeah. Yeah. exactly. So yeah, totally possible too.
In this context, how would they determine whether adding another parameter in a polynomial is better or worse?
Okay, so here's where this sort of art comes in. I can start, the procedure that I can think of right now is I would start by doing the MLE, do the frequentist thing first, not worry about the parameters, uncertainty just yet. Start with the model structure. Model structure is how many polynomials to include inside the data, inside the model, right? So that is part of the model structure. So first figure out at what complexity am I really going to start overfitting? And then constrain on that. So this is where this art comes into place. Constrain on this model complexity thing. Am I overfitting it? How many polynomials does my overfitting start to show up? And then constrain that and then do the Bayesian inference. And this is not for dogmatic reasons, this is for pragmatic reasons. Because it always takes a lot longer to fit the Bayesian model, the full Bayesian model with more polynomials than it would be to just estimate the MLE. All right? Maximum likelihood estimator given the model structure. Okay? Any other questions? You probably could. Like if you had a function that took a discrete parameter that has like the hyperparameter, yes, you probably could try that. I've not tried that, but I can imagine that sort of working. Yeah. Okay.
So I think this is related to the questions, but if you had an array of models and you weren't sure which one was the right model, is the right answer to fit them and do the PPC test?
That's one way. One way you check the PPC. The other ones you look at like BIC, for example, Bayesian information criteria. There is actually a good model selection page on the PyMC3 docs that shows how we can do this. There's another criteria called the widely applicable information criterion, also implemented in PyMC3, so you don't have to worry about the math behind it. And sometimes, more practically speaking, what you'll find is for a given data set, there may be multiple models on which there's no practical difference between the WAICs or the BIC score or whatever, right? And so these are equivalent models. So then what do? Well, then we go back to qualitative knowledge at that point. We go back to qualitative knowledge and reason through the model, which one lets us do an intervention, right? Which model structure tells us more clearly what we can intervene on our system, for example. All right, anything else? Okay, so before we end, I would like you to open up Slack. There's a link to a survey. This being the first time that Hugo and I have done this tutorial, we would really love to get some feedback. I've done this for the network analysis tutorial, and over time it's gotten better and better and better, and so future classes have benefited from the feedback that we get. And so I'd really like to collect how we can make this tutorial a little bit more informative, useful for future participants. So please open up Slack. There's a link to a Typeform survey. If you don't have Slack open right now, no worries. I will send it out to, let's see, I will put it on the GitHub repository as well, like a link to the Typeform survey. So I'd really like to have you fill out that survey right now so that we can figure out how we can make this tutorial better. Do we have any other questions surrounding, while people are doing the survey, do we have any other questions around so-called, more generally speaking, Bayesian modeling, Bayesian methods, and the likes? Let me see. I think, what do you mean by do we have to be able to solve? Oh, okay. So given the system of equations, do we have to be able to solve for y? There's this thing I'm sort of like hazy on right now, but it's how is your model underspecified, for example, or over? I'm blanking. What do you call that? Identifiability of the model. That's the thing. So is your model identifiable given the parameters and the data points on hand? That has to be a criteria that is fulfilled. That is to say, yes, we have to be able. So if you think about the curve fit scenario, if you were to do a deep neural network on like 3 data points, then your model is definitely not identifiable. So there are multiple sets of multiple parameter values for your thetas, your weights inside your neural network model that would fit these three points from the decay curve. So you really wouldn't want to fit that, for example. So anything you can think of from like non-Bayesian land, like just from a pure mathematical standpoint, like can I solve for y? Yes. If we can solve for y, then this is a good next step to take. Any other questions or things you want to discuss?
I'm just wondering if you know of any examples, and maybe we can put this in Slack too, of using something like PyMC3's Bayesian approaches for forecasting. Oh,
forecasting. So time series stuff, right? Yeah, everyone wants to know the future. Who's going to win the World Cup? I don't know if it's not Belgium, right? Belgium has already been knocked out. Yeah, okay, so Belgium's out. I have seen examples in the PyMC3 docs of using Gaussian processes for forecasting. We of course know that Gaussian processes have their own mean reversion problem. They all tend to go back to the mean value. But that is one resource out there. Thomas Wiki writes a lot on his blog about like finance stuff. So he has this time series modeling set of examples on his blog that you can take a look at. Forecasting is tricky, right? Because philosophically, not mathematically, philosophically, we're assuming the future looks like the past or in the present. And if that assumption is broken, then we fundamentally can't forecast at all, unless we can forecast the parameters that govern the future. So yeah, so there are examples, but keep in mind they always have that core assumption that past looks like the future.
But if you have a forecast, you have a forecast, right?
Yeah, if you have a forecast, you have a forecast under the assumptions of the model. Exactly. And you can do it with uncertainty. And I've done that at work as well. All right. If there are no other questions, thank you for coming. Thank you for sticking all the way through to, what time is it? 5:20, right? It's 4 tutorials. You've done a lot. You've heard a lot of people speak. Thanks also for Hugo to co-teach this tutorial. See you at the reception.